Hello there, and welcome back to the Science Sleepy Minds. Tonight you're standing on a sun-scorched launchpad in Cape Canaveral, Florida, and the year is 1977. The air is thick with salt and rocket fuel, and the particular kind of nervous optimism that only exists when human beings are about to fling something impossibly small into something impossibly large. Two identical spacecraft, each roughly the size of a compact car, sit atop their respective Titan IIIe rockets, waiting to be hurled into the outer solar system at speeds that would make a bullet feel inadequate. You are about to follow them. You're about to ride alongside Voyager 1 and Voyager 2 on a journey that spans planets, moons, rings, magnetic fields, volcanic eruptions, underground oceans, and eventually the very edge of the sun's influence itself. You probably will not survive this, not because it is dangerous, but because it is so wonderfully, impossibly long that your eyelids will surrender somewhere around Saturn, and that is perfectly fine. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, drop a comment telling me where you're listening from and what time it is where you are. I always love reading those. Someone is always tuning in at 3 in the morning from a place I've never heard of, and that is beautiful. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You need to understand something about the late 1970s. The space program is not exactly riding a wave of public enthusiasm. The Apollo missions ended a few years earlier, budgets are tightening, and NASA is scrambling to prove that unmanned exploration can still capture the public imagination. But there is a secret weapon hiding in the orbital mechanics of the outer solar system, and it comes in the form of a rare planetary alignment that occurs roughly once every 176 years. Jupiter, Saturn, Uranus, and Neptune are slowly drifting into a configuration that allows a single spacecraft to use the gravity of each planet to slingshot itself to the next, like a cosmic pinball machine. Miss this window, and you wait nearly 2 centuries for another shot. Researchers still debate whether the mission would have ever been funded without this alignment, because the original vision, called the Grand Tour, was even more ambitious and significantly more expensive than what eventually launched. You're standing in the sticky Florida heat watching technicians crawl over the rocket that will carry Voyager 2. And yes, you read that correctly. Voyager 2 launches first on August 20th, 1977. Voyager 1 follows 16 days later on September 5th. The naming is not a bureaucratic error. It is because Voyager 1 is on a faster trajectory and will actually reach Jupiter first, despite leaving Earth second. Think of it like 2 cars leaving a parking lot. The second car out takes the highway while the first car meanders along a scenic route. They are both heading to the same city, but the highway driver arrives first. NASA, in its infinite fondness for confusing the public, numbered them by arrival order rather than launch order. So tonight, whenever you hear Voyager 1, remember it is the speedy younger sibling that left home second, but overtook its older brother in the dark. Each spacecraft weighs about 815 kilograms and carries a suite of scientific instruments that, by today's standards, would make your smartphone snicker. The onboard computers have roughly 69 kilobytes of memory. For perspective, that is less than a single thumbnail image on a modern web page, and yet these machines will photograph entire worlds in detail never before seen. Map magnetic fields stretching millions of kilometers, analyze atmospheric compositions, and detect rings around planets that nobody knew had rings. There is a quirky detail here that engineers love to share. The data transmission rate from the outer solar system is about 160 bits per second, which is roughly 1/40,000th the speed of a slow home internet connection. Downloading a single high-resolution image from Neptune would take most of a workday. Patience, it turns out, is the most critical piece of technology on the entire mission. But the instruments are not the most famous cargo. Bolted to the side of each spacecraft is a golden phonograph record, a 12-inch gold-plated copper disc enclosed in an aluminum cover, complete with a stylus and pictographic instructions for any extraterrestrial civilization that might stumble upon it. The record contains 115 images, greetings in 55 languages, a selection of natural sounds from Earth including thunder, birdsong and whale calls, and 90 minutes of music ranging from Bach to Chuck Berry. The whole project was spearheaded by Carl Sagan, who assembled a small committee and gave them an almost absurd task: represent the entirety of human civilization on a single record that must be playable by beings who have never seen a human, heard a language, or held a record player. Scholars still argue whether the Golden Record is a genuine scientific communication tool or simply the most poetic piece of performance art ever launched into the void. Either way, it is out there right now, sailing through interstellar space, waiting. You watch the Titan rocket ignite beneath Voyager 2. The platform trembles. The sound hits your chest before it reaches your ears, a rolling, crackling thunder that feels less like noise and more like the atmosphere itself being torn open. The rocket climbs, tilts, and within minutes it is a bright point vanishing into the Atlantic sky. 16 days from now, Voyager 1 will follow the same blazing arc. Both spacecraft will spend the next 2 years coasting through the inner solar system, picking up speed, adjusting course with tiny thruster bursts, and aiming for a date with the largest planet in the neighbourhood. You tilt your head back, watch the exhaust trail dissolve into blue, and realise that you have just witnessed the beginning of the longest road trip in human history. The car has about 69 kilobytes of memory, no GPS, and a golden mixtape riding shotgun. What could possibly go wrong? You coast through the inner solar system for nearly 2 years, and honestly, not much happens. There is a lot of empty space between Earth and Jupiter, about 628 million kilometres, depending on where the planets are in their orbits, and you spend most of that time drifting in silence. The sun slowly shrinks behind you. Earth becomes a dot, then a memory. The spacecraft hums quietly, its instruments in a kind of electronic slumber, waking occasionally to calibrate and phone home. You try to appreciate the vastness, but vastness, it turns out, is mostly just waiting. Think of the longest road trip you've ever taken, then multiply it by about 4 million. That is roughly the vibe. But then Jupiter begins to grow in the camera frame and everything changes. Voyager 1 makes its closest approach to Jupiter on March 5th, 1979, passing within about 349,000 kilometers of the planet's cloud tops. Voyager 2 follows a few months later in July, and what they see transforms Jupiter from a striped marble in a textbook into a living, screaming, impossibly violent world. You're riding alongside Voyager 1 as the cameras begin resolving details that no Earth-based telescope has ever captured, and the first thing that overwhelms you is the sheer scale of the Great Red Spot. You have seen illustrations, you have read that it is a storm, but nothing prepares you for watching it resolve into a swirling anticyclonic vortex wider than 2 Earths placed side by side. The colours are not the flat orange of your childhood science poster. They are layered, amber and rust and cream and something close to salmon, all braided together in counter-rotating bands that shear against each other with a kind of slow, hypnotic violence. Wind speeds at the edges of the spot exceed 400 kilometers per hour, which is comfortably faster than any hurricane ever recorded on Earth, and this storm has been raging for at least 350 years, possibly much longer. Astronomers noted a persistent red spot on Jupiter as far back as the 1600s. though researchers still argue whether the spot observed by Giovanni Cassini in 1665 is the same feature Voyager photographed or a predecessor that faded and was replaced by a new one. Either way, you're staring at a storm older than the United States, older than the steam engine, older than calculus. It simply refuses to stop. You pull back and look at the broader atmosphere, and it is just as astonishing. Jupiter's famous bands, the alternating light zones and dark belts, are not static stripes. They are jet streams, rivers of ammonia and hydrogen gas flowing in opposite directions at different latitudes, creating turbulent boundaries where smaller storms spin off like eddies in a river. Voyager's cameras captured dozens of these smaller vortices, white ovals and brown barges tumbling along the belt zone boundaries, merging, splitting, and occasionally being swallowed by the great red spot like snacks. One quirky detail that planetary scientists love. Some of these smaller storms are themselves larger than Earth. A storm that could engulf your entire planet is, in Jovian terms, a minor weather event. Jupiter does not do anything small. The atmosphere itself is a puzzle wrapped in ammonia clouds. Voyager's instruments detect 3 distinct cloud layers: an upper deck of ammonia ice crystals, a middle layer of ammonium hydrosulfide, and a lower layer thought to be water ice, though that deepest layer remains somewhat speculative even decades later. The colours, those gorgeous reds, oranges and browns, are still not fully explained. Scientists believe they result from complex photochemistry, where ultraviolet sunlight breaks apart molecules in the upper atmosphere and recombines them into compounds called chromophores. But the exact recipe remains elusive. What specific molecules produce the great red spot's signature reddish hue? Phosphine, sulfur compounds, some exotic organic molecule? Researchers have been debating this since Voyager flew past, and they are still debating it now. You find it oddly comforting that a planet made almost entirely of hydrogen and helium can still keep secrets from the cleverest chemists on Earth. You also notice something that the cameras alone cannot capture, but the instruments scream about: lightning. Voyager detects powerful lightning strikes in Jupiter's atmosphere, predominantly on the night side of the planet, crackling through the clouds with energies far exceeding terrestrial bolts. The lightning appears concentrated in regions of active convection, where warm gas from the deep interior rises and collides with cooler layers above, much like thunderstorms on Earth, but scaled up to Jovian proportions. There is a mainstream fact here that is worth savouring. Before Voyager, many scientists assumed that lightning was a phenomenon unique to rocky planets with water-based weather systems. Jupiter shattered that assumption. Lightning, it turns out, is a universal conversation between rising heat and falling cold, and it can happen in an atmosphere made of hydrogen just as easily as one made of nitrogen and oxygen. The universe is less picky about its fireworks than we assumed. As you orbit closer, you catch time-lapse sequences that Voyager assembles from hundreds of individual frames, and these are perhaps the most mesmerizing product of the entire flyby. Watching Jupiter's atmosphere in accelerated motion is like watching a living oil painting. The bands ripple, the storms rotate, the great red spot churns with a slow, almost meditative rhythm, its outer edges braiding into the surrounding jet streams while its core remains eerily stable. You could stare at these sequences for hours, and many scientists did exactly that, playing them on loop in darkened rooms at the Jet Propulsion Laboratory, while trying to build mathematical models that could explain the fluid dynamics of an atmosphere with no solid surface beneath it. Some of those models are still being refined today, because Jupiter, for all its apparent simplicity as a gas giant, behaves in ways that push the limits of computational fluid dynamics. You lean back from the camera feed, eyes half closed, and let the swirling bands blur into something almost abstract, almost musical, a slow rotation of colour and turbulence that feels less like weather and more like the planet breathing. The storms are magnificent, yes, but Jupiter has been saving its real surprise for a tiny moon that nobody was paying much attention to. You drift away from the planet's cloud tops and turn your gaze toward Io, the innermost of Jupiter's 4 large Galilean moons, and what you find there will become the single most electrifying discovery of the entire Voyager mission. It begins, as many great discoveries do, with someone looking at the data sideways. On March 9th, 1979, just days after Voyager 1's closest approach to Jupiter, a navigation engineer named Linda Morabito is processing images of Io to refine the spacecraft's trajectory. She enhances the contrast on a photograph of the moon's limb, the curved edge silhouetted against the blackness of space, and notices something peculiar. A bright umbrella-shaped plume rising approximately 270 kilometers above the surface. At first it looks like it could be an artifact, a glitch in the camera, a smudge on the lens of a spacecraft hurtling through deep space at tens of thousands of kilometers per hour. But it is not a glitch, it is a volcanic eruption, an active volcanic eruption on a world other than Earth. You're witnessing the first confirmed extraterrestrial volcanism in human history, and the sheer improbability of the moment is enough to make your breath catch even at this drowsy hour. Before Voyager, the prevailing assumption about small moons was that they were dead worlds, geologically frozen, cratered, boring. The logic was straightforward. Small bodies cool faster than large ones, and a moon the size of Io, roughly the diameter of Earth's own moon, should have exhausted its internal heat billions of years ago. There should be nothing happening on Io except the slow accumulation of impact craters. And yet here it is, erupting with a ferocity that makes Mount St. Helens look like a candle being blown out at a birthday party. Scientists at the Jet Propulsion Laboratory scramble to reconcile what they're seeing with what they thought they knew, and within weeks, a theoretical explanation emerges that is almost as astonishing as the eruption itself. The answer is tidal heating. Io orbits Jupiter at a distance of only about 422,000 kilometers, close enough that the planet's immense gravitational field creates significant tidal forces on the little moon. But it's not just Jupiter doing the pulling. Io is locked in an orbital resonance with 2 neighbouring moons, Europa and Ganymede. For every single orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This precise gravitational choreography prevents Io's orbit from circularizing, which means the tidal forces on Io are not constant. They flex the moon's interior like a rubber ball being squeezed and released with every orbit, generating enormous amounts of frictional heat deep inside. That heat has to go somewhere, and it goes out through volcanoes, hundreds of them. A few scientists, notably Stanton Peele, Patrick Casson and Ray Reynolds, had actually predicted this tidal heating mechanism in a paper published just days before the Voyager flyby, making it one of the most spectacularly timed theoretical predictions in the history of planetary science. Researchers still discuss whether the prediction would have received any attention at all without the immediate jaw-dropping confirmation from Voyager's cameras. You turn your full attention to Io's surface, and it looks like nothing else in the solar system. Forget the grey, cratered landscapes you associate with moons. Io is a riot of colour. Bright yellows, oranges, reds, whites and blacks, splashed across the surface in patterns that resemble a pizza, a comparison that became so popular among scientists that it entered the informal lexicon of planetary geology. The colours come from sulfur and sulfur dioxide in various allotropic and temperature-dependent forms, deposited and redeposited by volcanic eruptions that constantly resurface the moon. Io has essentially zero impact craters, not because it has not been hit, but because volcanic activity buries craters faster than the solar system can make new ones. The surface of Io is, geologically speaking, the youngest in the entire solar system. Everything you see has been laid down in the cosmically recent past, and it will be buried again soon by the next eruption. Voyager 1 identifies at least 9 active volcanic eruptions during its flyby, with plume heights ranging from about 60 kilometers to over 300 kilometers. The largest plume, from a volcanic feature called Perle, creates a deposit ring on the surface roughly the size of Alaska. The eruption temperatures, measured by Voyager's infrared instruments, suggest that some of Io's lavas are extraordinarily hot, possibly exceeding 1500 degrees Celsius, which would make them hotter than any lava currently erupting on Earth. This is a quirky and somewhat unsettling detail. A moon smaller than our own is producing lava hotter than anything our planet can manage. The exact composition of Io's hottest lavas remains debated. Some researchers argue for ultramafic silicate magmas similar to ancient komatiite lavas that erupted on Earth billions of years ago, while others suggest the temperature measurements might be complicated by interaction with sulfur compounds on the surface. The debate has simmered, much like Io itself, for decades. When Voyager 2 arrives at Jupiter a few months later, it photographs Io again and finds that the surface has already changed. Some eruption plumes have vanished, new ones have appeared, and the colourful deposits around volcanic centres have shifted visibly. In just 4 months, Io has redecorated. You're looking at a world in perpetual geological turmoil, a moon that never holds still, driven by the invisible hand of tidal forces squeezing its guts with metronomic precision every 42 hours as it completes another orbit around Jupiter. You linger for a moment, watching a plume arc gracefully above Io's limb in the Voyager photograph, a silent fountain of sulfur and gas rising in the vacuum of space with a slow-motion elegance that belies the violence of its origin. Somewhere beneath that colourful crust, molten rock is churning, pressurised, and finding its way upward through cracks and vents. It is terrifying and beautiful and profoundly alien, and it happened because 3 moons decided to dance in perfect rhythm around a planet made of gas. You file that image somewhere in the back of your drowsy mind and prepare to drift onward, because Io's neighbour is waiting, and she has secrets of her own buried under miles of ice. You leave Io's volcanic fury behind, though the sulphur-tinged glow still lingers in your peripheral vision, and you coast outward to the next Galilean moon. Europa is smaller than Io, roughly the size of Earth's moon, and at first glance it seems like the polar opposite of its volcanic sibling. Where Io is a screaming canvas of colour and eruption, Europa is quiet, almost suspiciously quiet. Its surface is dominated by water ice, and it gleams with a pale, slightly tawny brightness that makes it one of the most reflective objects in the solar system. If Io is a pizza, Europa is a cue ball, smooth, pale, and deceptively simple. But you know better than to trust first impressions in the outer solar system, because Voyager's cameras are about to reveal something on Europa's surface that will redirect the entire trajectory of astrobiology for decades to come. As Voyager 2 sweeps past Europa in July of 1979, the images that trickle back to Earth at that glacially slow data rate reveal a surface unlike anything previously seen on a planetary body. Europa is crisscrossed with an intricate network of dark lines, some stretching thousands of kilometers across the moon's face like veins on the back of a pale hand. These lineae, as scientists will come to call them, are fractures in the ice shell, cracks that have opened and refrozen and opened again over geological time. And here is what makes your sleepy brain sit up slightly. The surface is almost completely devoid of impact craters, just like Io, but for entirely different reasons. Io buries its craters under volcanic deposits. Europa appears to erase its craters by resurfacing from below, as though something beneath the ice is warm enough to heal the wounds inflicted by asteroid impacts. The implication is staggering. Beneath Europa's frozen crust, there may be a global ocean of liquid water. You let that sink in for a moment. Liquid water. On a moon orbiting Jupiter, nearly 800 million kilometers from the Sun, in a neighborhood so cold that the surface temperature hovers around minus 160 degrees Celsius, the Sun's warmth at this distance is roughly 1/27th of what Earth receives, barely enough to notice, certainly not enough to melt ice. So where is the heat coming from? The answer, as you might have guessed from your time at Io, is tidal heating. Europa participates in the same orbital resonance with Io and Ganymede, and while the tidal forces acting on Europa are weaker than those torturing Io, they are still significant enough to generate internal heat. Not enough heat to melt rock and produce volcanoes, but potentially enough to maintain a layer of liquid water between the rocky interior and the icy crust. Scientists still argue about the thickness of Europa's ice shell. Estimates range from a few kilometers to 30 or more, and the depth of the ocean beneath, which could be 60 to 150 kilometers deep. If the deeper estimates are correct, Europa contains roughly 2 to 3 times the volume of all Earth's oceans combined, locked away under a shell of ice on a moon you could drive across in a long weekend. Voyager's instruments are not sophisticated enough to confirm the ocean directly. That confirmation will come later, from the Galileo spacecraft in the late 1990s, which detects a magnetic signature consistent with a salty, electrically conductive liquid beneath the surface. But the seeds of the discovery are planted right here, right now, in these Voyager images of cracked ice and absent craters. You're watching the birth of a hypothesis that will reshape humanity's understanding of where life might exist beyond Earth. Before Europa, the habitable zone, the region around a star where liquid water can exist, was defined almost entirely by distance from the Sun. Too close and your water boils. Too far and it freezes. Earth sits in the sweet spot, and that was considered more or less the end of the conversation. Europa demolishes that tidy framework. If tidal heating can maintain liquid water on a moon orbiting a gas giant in the frozen outer solar system, then the habitable zone is not a narrow band around a star. It is everywhere gravity and orbital mechanics conspire to generate internal heat. The number of potentially habitable worlds in the galaxy does not just increase, it explodes. You zoom in on the fracture patterns, and they tell their own cryptic story. Some of the linear double ridges, parallel raised edges flanking a central trough, as though something has pushed up from below and cracked the surface apart. Others are bands where new ice appears to have filled in gaps, like tectonic spreading zones on Earth's ocean floor, but rendered in frozen water instead of basalt. There are regions called chaos terrain, where the surface looks like it has been shattered into irregular blocks, rotated and refrozen in new positions, as though the ice briefly lost its footing on the liquid beneath, and then solidified again in disarray. One particularly famous region, Connemara Chaos, looks almost exactly like broken pack ice in Earth's Arctic Ocean, and when scientists reassembled the blocks like a jigsaw puzzle, they found they could fit many of them back together, proving that the surface had indeed broken apart and drifted before refreezing. The resemblance to terrestrial sea ice is so striking that some researchers half-jokingly proposed sending a polar icebreaker to Europa, though the logistics of that particular field trip remain somewhat challenging. There is a scholarly debate that Voyager's images ignited and that continues to this day. Is Europa's ice shell thin enough that the ocean occasionally breaches the surface, or is it a thick, convecting glacier that never fully cracks through? The thin ice camp points to the chaos regions and the apparent mobility of surface blocks. The thick ice camp argues that solid-state convection within the ice shell can explain the resurfacing without requiring direct contact between the ocean and the surface. The distinction matters enormously for future missions hoping to sample Europa's ocean for signs of life. If the ice is thin and occasionally broken, ocean material may be accessible right on the surface. If the ice is a 40-kilometre thick barrier, you need a very ambitious drill. You pull back and gaze at Europa one last time, a small pale world that looks so serene from a distance, its cracked surface glowing faintly in reflected Jovian light. Somewhere beneath that ice, in pitch darkness, salt water may be lapping against a rocky seafloor warmed by tidal friction. And where there is liquid water and heat and rock, the basic ingredients for life as we understand it are present. You're not saying there are fish under Europa's ice. You're just saying that of all the places Voyager visited, this quiet little moon might be the one that matters most in the long run. You drift outward from Europa's cracked shell, the faint possibility of a hidden ocean still tugging at your imagination, and you set your sights on the two remaining Galilean moons. Ganymede and Callisto are the giants of Jupiter's moon system, the big quiet siblings who do not scream with volcanoes or whisper with subsurface seas, at least not as loudly. But Voyager's cameras will show you that even the quiet ones have stories worth hearing, and some of those stories will not make full sense for decades. Ganymede greets you first, and the initial impression is of a world caught between two identities. Roughly 1/3 of its surface is dark, ancient and heavily cratered, looking much like you would expect a dead moon to look. But the remaining 2/3 is younger, lighter terrain covered in an elaborate network of grooves and ridges that stretch across the surface like the tracks of some enormous celestial ice skate. These grooved terrains are evidence of past tectonic activity, a period in Ganymede's history when the ice shell was pulled apart and resurfaced by some internal process. The contrast between the two terrain types is dramatic. It is as though someone took a battered ancient world and renovated half of it, while leaving the other half untouched, like a house where the kitchen is brand new, but the living room has not been redecorated since the Eisenhower administration. Ganymede is the largest moon in the entire solar system, bigger than the planet Mercury, and Voyager's flyby gives scientists their first detailed look at a world that turns out to be far more complex than its quiet reputation suggests. The grooved terrain implies that Ganymede experienced significant internal heating at some point in its past, enough to mobilize its ice shell and create the tectonic features visible on the surface. But Ganymede does not sit in the same tight orbital resonance that drives Io's volcanism and Europa's potential ocean. Its tidal heating is much weaker. So what drove the resurfacing? Researchers still argue about this. Some propose that Ganymede passed through a more intense tidal heating phase early in its history when its orbital resonance with Io and Europa was evolving. Others suggest radiogenic heating from the decay of radioactive elements in its rocky core. The debate remains unresolved, a geological mystery frozen into the grooved ice of a moon that has since gone quiet. One thing Voyager cannot detect, but later missions will confirm, is that Ganymede possesses its own intrinsic magnetic field, the only moon in the solar system known to generate one. This discovery, made by the Galileo spacecraft in the 1990s, implies that Ganymede has a partially molten iron core much like Earth, churning with enough convective motion to generate a magnetic dynamo, a moon with its own magnetosphere. You file that away as one of the solar system's more delightful oddities, a world that is technically a moon but behaves, in some respects, like a miniature planet trapped in Jupiter's gravitational embrace. There is even evidence, again from later missions building on Voyager's groundwork, that Ganymede may harbour its own subsurface ocean, sandwiched between layers of ice at different pressures. The outer solar system, it seems, is practically swimming in hidden water. You leave Ganymede and glide further out to Callisto, the outermost of the 4 Galilean moons, and the mood shifts immediately. Callisto is the wallflower of the group, the moon that time seems to have forgotten. Its surface is among the most heavily cratered in the solar system, a battered ancient landscape that has changed very little in 4 billion years. Where Io erupts and Europa cracks and Ganymede grooves, Callisto simply sits there, accumulating impact scars with the patience of a park bench collecting pigeon droppings. There is no evidence of tectonic activity, no grooved terrain, no volcanic features. Callisto appears to be geologically dead, and it has been dead for a very long time. But even Callisto has its curiosities. Voyager's cameras reveal a massive multi-ring impact structure called Valhalla, a bright central region surrounded by concentric rings of ridges and troughs, extending outward for nearly 2,000 kilometers. Valhalla is one of the largest impact features in the solar system, a frozen record of a catastrophic collision that occurred billions of years ago. The concentric rings are thought to be the result of the icy crust fracturing and rebounding after the impact, like ripples frozen in place on a pond that was struck by a very large, very angry stone. There is a quirky detail about Valhalla that planetary scientists find endlessly amusing. Despite being an enormous impact scar, the central region is not a deep basin. It is actually relatively flat, even slightly elevated because the ice flowed back in after the impact and relaxed over geological time. Callisto's surface, being ice rather than rock, behaves almost like very slow silly putty on long timescales, gradually smoothing out sharp features while preserving the broader structure. Callisto's heavy cratering makes it an invaluable record of the bombardment history of the Jovian system. By counting craters and estimating their ages, scientists can reconstruct the rate at which objects have struck Jupiter's moons over time, which in turn tells you something about the population of comets and asteroids that have wandered through the outer solar system over the past 4 billion years. Callisto is essentially a history book written in bruises, and Voyager provides the first detailed photographs of its pages. Historians of planetary science still argue whether Callisto is truly dead or merely dormant. Later measurements by the Galileo spacecraft hinted at a possible subsurface ocean on Callisto as well, based on its magnetic response to Jupiter's rotating field, though the evidence is less compelling than for Europa or Ganymede. If Callisto does have an ocean, it would be deeply buried beneath a very thick ice shell, insulated from the surface by hundreds of kilometers of frozen water. The idea that even the most geologically inert moon in the Jovian system might harbour liquid water speaks to just how common subsurface oceans may be in the outer solar system. You gaze down at Callisto's battered face, every crater a timestamp, every ring a frozen ripple from an ancient catastrophe, and you appreciate the quiet dignity of a world that has simply endured. Not every moon needs to erupt or crack to be interesting. Some just need to remember. You take one last look at the 4 Galilean moons arrayed around Jupiter, Io burning, Europa cracking, Ganymede grooved, Callisto cratered, and you realise that Voyager has transformed them from 4 points of light in a telescope into 4 distinct worlds, each with its own geology, its own history, its own unanswered questions. Galileo himself, peering through his tiny refractor in 1610, could barely resolve them as dots. Now you have walked their surfaces in photographs, and the outer solar system has never felt so alive. You pull your attention back from the moons and refocus on Jupiter itself, because Voyager still has a couple of revelations tucked away that have nothing to do with the Galilean 4. The first is something that nobody seriously expected to find, a ring system around Jupiter. Before Voyager 1's arrival, rings were Saturn's thing. Saturn owned rings the way Paris owns the Eiffel Tower. It was the defining feature, the postcard image, the one thing even people who could not name a single moon could tell you about. The idea that Jupiter might also have rings had been loosely hypothesized by a few researchers, but there was no observational evidence, and most scientists would have bet their grant funding against it. So when Voyager 1's cameras deliberately aimed at the region around Jupiter's equatorial plane during the flyby, captured a faint, thin band of material encircling the planet, the reaction at the Jet Propulsion Laboratory was something between delight and disbelief. Jupiter's ring system is nothing like Saturn's majestic, icy spectacle. It is faint, wispy, and composed primarily of tiny dust particles, rather than the substantial chunks of ice and rock that make Saturn's rings so photogenic. The main ring is only about 30 kilometers thick and extends from roughly 122,000 to roughly 129,000 kilometers from Jupiter's center. There is an inner halo of material that puffs up into a thicker, more diffuse torus, and a pair of faint gossamer rings further out that are associated with the tiny moons Amalthea and Thebe. The particles in Jupiter's rings are so small, mostly in the micrometer range, that they are best seen when backlit by the sun, which is exactly the geometry Voyager exploited by photographing the rings from Jupiter's far side. In forward scattered light, the tiny grains light up like dust motes in a sunbeam, and suddenly a ring system that is essentially invisible from Earth reveals itself in ghostly, ethereal beauty. The origin of Jupiter's rings is fundamentally different from Saturn's. Rather than being ancient remnants of the planet's formation or the debris of a shattered moon, Jupiter's rings are continuously replenished. Micrometeorite impacts strike the small inner moons, Metis, Adrastea, Amalthea and Thebe, and blast tiny particles off their surfaces into orbit around Jupiter. These particles slowly spiral inward due to various drag forces and are eventually swallowed by the planet's atmosphere, which means the rings would vanish entirely if the source moons were removed. The whole system is a steady-state process of creation and destruction, a conveyor belt of dust that happens to form a ring only because the impacts keep coming. Researchers still debate the precise balance between particle creation and removal rates, and whether the ring's appearance has changed significantly over geological timescales or remains roughly constant. There is something philosophically appealing about a ring system that is not a relic but a process, not a monument but a conversation between moons and meteorites that never quite finishes. You file Jupiter's rings away as one of those discoveries that fundamentally shifts your assumptions about what is possible in planetary systems. Before Voyager, rings equaled Saturn. After Voyager, rings became a feature that any giant planet might possess, and indeed, Voyager will go on to discover ring systems around Uranus and Neptune as well. The solar system, you are learning, is far more generous with its jewellery than anyone suspected. But the rings are only the appetizer. The main course of Voyager's non-moon Jupiter science is the magnetosphere, and it is, without exaggeration, the single largest coherent structure in the solar system after the Heliosphere itself. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, generated by currents of metallic hydrogen swirling deep in the planet's interior under pressures so extreme that hydrogen stops being a gas and starts behaving like a liquid metal. The resulting magnetosphere, the bubble of space dominated by Jupiter's magnetic field, extends millions of kilometers in every direction. On the side facing the Sun, it is compressed by the solar wind to a boundary roughly 3 to 7 million kilometers from the planet. On the opposite side, the magnetotail stretches away from the Sun for at least 750 million kilometers, possibly extending all the way to Saturn's orbit. If you could see Jupiter's magnetosphere with your naked eyes, it would appear larger than the full moon in Earth's sky, despite being hundreds of millions of kilometers farther away. That is a staggering piece of trivia to carry around, and you may use it at your next dinner party if you enjoy watching people's expressions go blank. Voyager's instruments map this magnetosphere in unprecedented detail, measuring the charged particle environment, the plasma densities, the magnetic field strength and orientation at various distances from the planet. One of the most significant findings involves Io, because that volcanic little moon is not just passively orbiting inside the magnetosphere, it is actively feeding it. Io's volcanoes blast roughly 1 ton of sulfur dioxide and other volcanic gases into space every second, and this material is quickly ionized by Jupiter's radiation belts, becoming a plasma that is swept up by the rotating magnetic field and distributed into a donut-shaped torus encircling Jupiter at Io's orbital distance. This Io plasma torus is one of the most intense radiation environments in the solar system, and it links the volcanic activity on Io's surface directly to the behaviour of Jupiter's magnetosphere in a feedback loop that scientists found both elegant and terrifying. Particles from the torus spiral along magnetic field lines and slam into Jupiter's polar atmosphere, generating auroras that are hundreds of times more powerful than any on Earth. Voyager detects these auroras in ultraviolet light, shimmering crowns of energy draped over Jupiter's poles, powered not primarily by the solar wind as on Earth, but by the volcanic breath of a tortured moon. You sit quietly as the data streams in, watching numbers and graphs translate into a picture of a planet that dominates its local environment in ways that border on the imperial. Jupiter does not just have moons, it rules them. It heats them, irradiates them, strips material from their surfaces, and weaves that material into its own magnetic architecture. You're beginning to understand that the Jovian system is not a planet with accessories. It is a miniature solar system unto itself, with Jupiter as the central engine driving everything around it. And you have barely left the first stop on the itinerary. You leave Jupiter's magnetic empire behind, and the spacecraft settle into another long coast, this time toward the ringed jewel of the solar system. Saturn has been waiting patiently, and you can almost feel its gravitational pull growing stronger as the months tick by. Voyager 1 arrives first, making its closest approach on November 12, 1980. Voyager 2 follows on August 26, 1981. And if Jupiter was the loud, boisterous introduction to giant planet science, Saturn is the elegant, breathtaking encore that steals the entire show. You already know Saturn has rings. Everyone knows Saturn has rings. Galileo spotted something odd about the planet through his telescope in 1610, though he described it as having ears rather than rings, because his optics were not sharp enough to resolve the true geometry. Christian Huygens figured out the ring structure in 1655, and since then, ground-based telescopes have steadily improved our view, revealing a handful of broad divisions: the A-ring, the B-ring, the famous Cassini division gap between them, the fainter C-ring closer to the planet. By the time Voyager launches, scientists have a reasonable mental model of Saturn's rings: a few broad, flat structures made of ice particles, separated by a few gaps caused by gravitational resonances with Saturn's moons. It is a tidy picture. Voyager demolishes it completely. As Voyager 1 closes in on Saturn, the cameras begin resolving the rings at higher and higher resolution, and what emerges is not a few broad bands, but an almost incomprehensible wealth of fine structure. The broad rings dissolve into thousands upon thousands of individual ringlets, nested so closely together that the entire system resembles the grooves on a vinyl record, which is a fitting comparison given that the spacecraft is literally carrying one. The B-ring alone, the brightest and densest of the main rings, contains so much fine structure that scientists initially struggle to count the individual features. Estimates range into the tens of thousands of distinct ringlets, each one a narrow stream of icy particles orbiting Saturn in nearly perfect circles, separated from its neighbours by gaps that can be as narrow as a few kilometres. The visual effect is hypnotic. You're looking at a structure that spans nearly 300,000 kilometres from edge to edge, but is only about 10 metres thick in most places. If you scaled Saturn's rings down to the diameter of a football field, they would be thinner than a razor blade. That particular comparison has been repeated so often in popular science that it borders on cliché, but it remains genuinely astonishing every time you actually pause to absorb it. The fine structure raises immediate questions. Why so many ringlets? What maintains the boundaries between them? Why don't the particles just smear out into a uniform disk over time? Some of the gaps are explained by orbital resonances with Saturn's moons. The Cassini division, for example, is maintained largely by the gravitational influence of the moon mimas, which tugs particles out of that region the same way a parent pulls a child away from a puddle. But many of the finer ringlets and gaps have no obvious resonance explanation, and researchers still debate the mechanisms that maintain them. Some may be caused by tiny embedded moonlets, too small for Voyager to photograph, that carve channels through the ring material like boats leaving wakes in a river. Others may result from self-organizing dynamics within the ring particles themselves, a kind of collective behavior emerging from the interactions of billions of individual ice chunks following the basic laws of gravity and collision. The rings, it turns out, are not just a pretty structure. They are a vast natural laboratory for studying the physics of disk systems, and the lessons learned from Saturn's rings have been applied to everything from protoplanetary disks around young stars to the dynamics of galaxies. Voyager also discovers features within the rings that are genuinely weird. The F-ring, a narrow ring just outside the main ring system, is braided. Two or more strands of ring material appear to twist around each other like a loosely wound rope, a configuration that should not be stable under normal orbital mechanics. The braiding is caused by the gravitational influence of two small shepherd moons, Prometheus and Pandora, which orbit just inside and outside the F-ring and perturb its particles into these strange configurations. Voyager's images of the braided F-ring cause considerable excitement and confusion at the Jet Propulsion Laboratory, because nobody had predicted anything quite like it. There is a mainstream historical fact hiding in this discovery. The concept of shepherd moons, small satellites whose gravity confines ring material into narrow bands, was theoretically proposed before Voyager, but had never been observationally confirmed. Voyager's discovery of Prometheus and Pandora flanking the F-ring provides the first direct evidence that the mechanism actually works, validating a neat piece of theoretical celestial mechanics with real photographs. Then there are the spokes, dark radial features that appear and disappear in the B-ring, stretching outward from the planet like the spokes of a wheel. They should not exist. In a system governed by Keplerian orbital mechanics, inner particles orbit faster than outer particles, which means any radial feature should be sheared apart almost immediately by differential rotation. And yet the spokes persist for hours, rotating with the planet's magnetic field rather than with the orbital speed of the ring particles. The leading explanation involves charged dust particles being levitated above the ring plane by electrostatic forces linked to Saturn's magnetosphere, creating a temporary structure that is coupled to the magnetic field rather than to the orbital dynamics. Researchers still argue about the exact mechanism, and the spokes remain one of the more enchanting, unsolved puzzles in planetary ring science. You watch them drift across the B-ring in Voyager's time-lapse sequences, ghostly radial shadows that appear at dawn on the rings and fade by afternoon, as though Saturn's rings are breathing in some slow electromagnetic rhythm that nobody has quite decoded. You lean back and let the image of those impossibly thin, impossibly detailed rings fill your vision, thousands of ringlets gleaming in reflected sunlight, braided strands twisting in the F-ring, phantom spokes drifting like whispers across the B-ring. Saturn is not just beautiful, it is intricate in a way that borders on the mathematical, a world dressed in its own physics, and Voyager has pulled back the curtain just enough to show you how little we understood before we actually went there. You're still marvelling at the rings when Voyager 1 pivots its cameras toward a world that will fundamentally alter the mission's trajectory, both literally and scientifically. Titan, Saturn's largest moon, has been a source of fascination and frustration for astronomers since Gerard Kuiper detected methane in its atmosphere back in 1944. The mere existence of an atmosphere on a moon was extraordinary. No other moon in the solar system had revealed one, and the tantalizing question of what Titan's atmosphere actually looked like up close had been simmering in the planetary science community for decades. Voyager 1 is about to provide the answer, and the answer is going to cost something. As Voyager 1 approaches Titan on November 12th, 1980, the cameras strain to resolve surface features through the atmosphere, and what they find is a wall. A thick, opaque, orange-brown haze envelops the entire moon from pole to pole, completely obscuring the surface beneath. There are no gaps, no clearings, no convenient windows in the smog. Titan is wrapped in a photochemical fog so dense that Voyager's visible light cameras cannot penetrate it at all. The surface of Titan remains as hidden after the flyby as it was before, which is simultaneously one of the mission's biggest disappointments and one of its most profound revelations, because what the instruments do detect about the atmosphere itself is staggering. Titan's atmosphere is composed primarily of nitrogen, roughly 95%, making it the only body in the solar system besides Earth with a predominantly nitrogen atmosphere. The remaining few percent is mostly methane, with traces of ethane, acetylene, hydrogen cyanide, and a smorgasbord of complex organic molecules produced by photochemistry in the upper atmosphere. The surface pressure is about 1.5 times Earth's sea level pressure, which means that if you were standing on Titan's surface you would feel slightly more atmospheric weight on your shoulders than you do walking around on Earth. This is deeply counterintuitive for a moon. Titan is smaller than Earth, with much weaker gravity, and yet it has managed to hold on to an atmosphere denser than our own. The explanation lies partly in Titan's low temperature. Surface temperatures hover around -179 degrees Celsius, which slows the thermal velocity of gas molecules and makes them less likely to escape into space, and partly in the relatively calm solar wind environment at Saturn's distance from the Sun. Titan keeps its atmosphere because it is cold enough and sheltered enough to hold its breath. The orange haze that blocks Voyager's cameras is produced by a process that scientists find both familiar and alien. Ultraviolet sunlight and energetic particles from Saturn's magnetosphere break apart methane and nitrogen molecules in the upper atmosphere, and the resulting fragments recombine into increasingly complex organic compounds, tholins, as Carl Sagan would later name them. These tholins form a photochemical smog that settles slowly downward, accumulating in layers and eventually raining onto the surface as a fine organic sediment. You're looking at a world where it rains organic chemistry, where the sky is literally producing the molecular building blocks of biochemistry and depositing them on the ground. The implications for prebiotic chemistry are tantalizing. Researchers still debate whether Titan's surface conditions, extremely cold, devoid of liquid water on the surface, are too hostile for any meaningful chemistry to progress toward biology, or whether the sheer abundance and variety of organic molecules might enable chemical processes that nobody has imagined yet. Titan, in a sense, is running a planetary-scale experiment in organic chemistry, and it has been running it for billions of years. Here is the quirky and somewhat poignant detail that defines Voyager 1's encounter with Titan. NASA chose to fly Voyager 1 so close to Titan that the gravitational deflection would fling the spacecraft out of the plane of the solar system entirely. This was a deliberate sacrifice. By optimizing the Titan flyby for maximum scientific return, mission planners accepted that Voyager 1 would be unable to continue onward to Uranus and Neptune. The trajectory that gave the best Titan science was geometrically incompatible with a further planetary tour. Voyager 1 traded the rest of the Grand Tour for a close look at an atmosphere it could not even see through. That decision tells you something about how scientifically important Titan's atmosphere was considered to be. Researchers at the time argued passionately about whether the trade-off was worth it, and historians of the space program still discuss whether an alternative trajectory could have delivered adequate Titan science while preserving the option to visit Uranus. In the end, the atmosphere won. Voyager 1 swooped past Titan, gathered its precious data, and was hurled upward out of the ecliptic plane, its planetary mission effectively over. From this point forward, only Voyager 2 carries the burden of the Grand Tour. The data from the Titan flyby directly inspires the Cassini-Huygens mission, which arrives at Saturn in 2004 and drops a probe through Titan's atmosphere to the surface in January 2005. That probe, riding down through the orange haze on a parachute, finally reveals what Voyager could not see: a landscape of methane lakes, hydrocarbon dunes, icy pebbles, and river channels carved by liquid methane rain. Every one of those discoveries has its roots in the frustrating, tantalizing wall of orange smog that greeted Voyager 1 in November of 1980. The mission that could not see Titan's surface ensured that a future mission would. You sit with that for a moment, the idea that sometimes the most important discovery is the discovery of what you cannot yet know. Voyager 1 gave up planets for an atmosphere it could not penetrate, and in doing so catalyzed a chain of exploration that continues to this day. There is a lesson in that about patience, about the long game of science, about sending one spacecraft to ask the question so that another can eventually find the answer. You watch Titan's orange disk recede in the rear camera, a world swaddled in its own chemistry, patient and opaque, and you let Voyager 1 climb away from the ecliptic plane on its new, lonely trajectory while you hitch your ride with Voyager 2, which still has planets to visit and secrets to uncover. You settle into Voyager 2's frame of reference as it sweeps through the Saturn system, and while its older sibling is climbing away into the cosmic north, Voyager 2 has unfinished business among the rings and moons. The Titan close-up belongs to Voyager 1, but Voyager 2 has the luxury of a broader tour, and it uses that freedom to catalogue a menagerie of smaller moons that turn out to be far stranger than anyone anticipated. Saturn, you're discovering, does not just have rings, it has an entire circus of tiny gravitational performers orbiting within, around, and between those rings, and each one has its own peculiar act. Start with Enceladus, a moon barely 500 kilometers across that Voyager, 2 photographs during its August 1981 flyby. The images reveal a surface that is, in places, almost impossibly smooth. Vast plains of fresh ice with very few craters, suggesting that the surface has been resurfaced recently in geological terms. There are also regions of grooves and fractures that hint at tectonic activity, though Voyager's resolution is not quite high enough to tell the full story. Scientists note the unusual brightness of Enceladus, which reflects nearly 100% of the sunlight that hits it, making it one of the most reflective objects in the solar system. Something is keeping Enceladus clean and bright, and while Voyager cannot determine what that something is, the suspicion begins to form that this little moon might be geologically active. That suspicion will be spectacularly confirmed decades later by the Cassini spacecraft, which discovers geysers of water ice and vapour erupting from fractures near Enceladus's south pole, feeding material directly into Saturn's E-ring. But here, in 1981, you're looking at the first breadcrumbs of that discovery. A small moon that is too smooth, too bright, and too young-looking to be geologically dead. Remember Europa and its suspicious lack of craters. Enceladus is playing the same game, and the outer solar system's collection of secretly active little worlds is growing. Then there are the shepherd moons, those tiny gravitational wranglers you encountered braiding the F-ring. Prometheus and Pandora orbit just inside and outside the F-ring respectively, and their combined gravitational influence confines the ring material into its narrow band, while simultaneously creating the strange braided and kinked structures that so baffled scientists. Voyager's images of these two moons reveal irregularly shaped potato-like bodies only a few tens of kilometers across, far too small to be spherical under their own gravity. They are essentially flying rubble piles, yet their gravitational fingerprints on the F-ring are precise and measurable. There is a satisfying elegance to the shepherd moon concept, the idea that ring-sharp edges are not maintained by some mysterious force, but by the gentle, persistent gravitational nudging of tiny moons patrolling the boundaries like cosmic border collies herding ice particles. Voyager 2 also captures images of a pair of moons that engage in one of the solar system's most charming orbital dances. Janus and Epimetheus share nearly the same orbit around Saturn, separated by only about 50 kilometers in orbital radius. Every 4 years, the inner moon catches up to the outer moon, and instead of colliding, they swap orbits. The inner moon's gravitational pull speeds up the outer moon, pushing it into a slightly higher orbit, while the outer moon's pull slows the inner moon, dropping it into the lower orbit. They trade places, and then spend the next 4 years slowly approaching each other again for another swap. This gravitational do-si-do has been going on for millions of years, two tiny moons perpetually exchanging positions in a dance that is as mathematically precise as it is whimsical. Scholars still debate the long-term stability of this co-orbital configuration, and whether it represents a common outcome in moon system dynamics, or a rare and fragile arrangement unique to Saturn. Either way, it is one of those discoveries that makes orbital mechanics feel less like mathematics and more like choreography. You also catch glimpses of Mimas, a moon roughly 400 kilometers in diameter, whose most prominent feature is a colossal impact crater named Herschel that spans nearly 1/3 of the moon's entire diameter. The crater gives Mimas an uncanny resemblance to the Death Star from Star Wars, a comparison that was immediately and inevitably made by everyone who saw the photographs, even though Mimas predates the fictional battle station by several billion years. The impact that created Herschel must have come perilously close to shattering Mimas entirely. A slightly larger or faster impactor would have reduced the moon to a cloud of rubble, and you would be looking at another ring instead of another moon. There is a quirky bit of trivia embedded in this near miss. Mimas is the smallest known astronomical body that is still rounded by its own gravity, sitting right at the threshold between a world that can pull itself into a sphere and a world that remains an irregular chunk. It is the minimum viable moon, the smallest thing in the solar system that can credibly call itself round. Hyperion is another oddity that Voyager captures, an irregularly shaped moon about 270 kilometers across that tumbles chaotically through space, rather than rotating in the orderly fashion of most moons. Its rotation is genuinely unpredictable, a real-world example of chaotic dynamics, meaning that if you visited Hyperion twice, the orientation of its surface relative to Saturn would be different in a way that no simple calculation could forecast. It is one of only a handful of objects in the solar system known to exhibit true chaotic rotation, and its sponge-like, crater-pocked surface gives it the appearance of something that has been chewed on by the cosmos and spat out. You lean back and consider the parade of small moons Voyager 2 has revealed. Shepherds sculpting rings, co-orbitals swapping places, a Death Star impersonator, a chaotically tumbling sponge, and a suspiciously smooth little world that might be hiding geysers. Saturn's moon system is not just a collection of orbiting rocks. It is an ecosystem of gravitational interactions, each moon influencing its neighbours, shaping the rings, and occasionally doing something so unexpected that entire theoretical frameworks have to be rewritten. The Voyager team catalogues new moons, refines orbits, and feeds the data into models that will keep scientists busy for decades. And Voyager 2 still has 2 planets left to visit. Planets that no spacecraft has ever seen up close, waiting in the cold, dark reaches of the outer solar system. You wave goodbye to Saturn's circus of moons and rings, and Voyager 2 settles into the longest, loneliest coast of the entire mission. The gap between Saturn and Uranus is vast, roughly another 1.5 billion kilometers of nothing, and the transit takes 4.5 years. Think about that for a moment. 4.5 years of drifting through empty space, instruments mostly quiet, the sun shrinking to a bright star behind you, the temperature dropping, the light dimming. The spacecraft is aging, its plutonium power source is slowly decaying, producing a little less electricity each year. Its thrusters have already fired thousands of times for a course, corrections and attitude adjustments, consuming irreplaceable hydrazine fuel. And the engineering team back on Earth is facing a problem that nobody fully appreciated when the mission launched. Voyager 2's scan platform, the motorized turntable that aims the cameras and instruments, jammed briefly during the Saturn flyby, probably due to excessive slewing, and although it was coaxed back into service, there is a lingering anxiety that it might fail again at Uranus, leaving the cameras pointed uselessly into the void. Engineers develop new, slower slewing procedures to baby the mechanism, and they hold their breath for 4.5 years. On January 24, 1986, Voyager 2 makes its closest approach to Uranus, passing within about 81,000 kilometers of the planet's cloud tops. It is the first and, as of tonight, still the only spacecraft ever to visit Uranus. Every photograph, every measurement, every data point humanity possesses about Uranus from close range comes from this single flyby, by a machine that was not originally designed to go this far. The encounter window is brief. The geometry of the flyby means that most of the useful science has to be collected in a span of roughly 6 hours, as Voyager screams past at nearly 72,000 kilometers per hour. There is no loitering, no second pass, no chance to go back and rephotograph something that came out blurry. You get one shot, and then Uranus recedes into the dark forever. The first thing that strikes you about Uranus is how profoundly bland it appears. After Jupiter's screaming bands and Saturn's intricate rings, Uranus presents itself as a nearly featureless blue-green sphere. The colour comes from methane in the upper atmosphere, which absorbs red wavelengths of sunlight and reflects blue and green back to the camera. But where are the storms? Where are the bands? Where is the atmospheric drama? Voyager's cameras, straining at the limits of their sensitivity in the feeble sunlight, Uranus receives only about 1/400th the solar energy that Earth does, reveal an atmosphere that is almost eerily calm on the surface. A few faint cloud features are detected after extensive image processing, but compared to Jupiter and Saturn, Uranus looks like a planet that has simply given up on weather. Scientists dub it the most boring planet in the solar system, a reputation that will stick for years and that Uranus frankly does not deserve, because beneath that placid exterior things are deeply strange. The most immediately obvious strangeness is the tilt. Uranus rotates on its side. Its axial tilt is approximately 98 degrees, meaning its poles take turns pointing almost directly at the Sun over the course of its 84-year orbit. At the time of Voyager's flyby, the South Pole is aimed nearly at the Sun, which means the entire southern hemisphere has been in continuous daylight for decades, while the northern hemisphere has been in continuous darkness. No other planet in the solar system behaves like this, and the leading explanation is that sometime early in its history, Uranus was struck by an Earth-sized protoplanet that knocked it onto its side. Researchers still argue about whether this was a single catastrophic impact or a series of smaller collisions that gradually tilted the planet over time. There is even a minority hypothesis suggesting that the tilt resulted not from an impact, but from gravitational interactions with other planets during the chaotic early rearrangement of the solar system, though this remains less widely accepted. The tilt has consequences that ripple through every aspect of the Uranian system. The magnetic field, which Voyager measures for the first time, turns out to be tilted roughly 60 degrees from the rotational axis and offset from the planet's centre by about 1/3 of Uranus's radius. On Earth, the magnetic field is roughly aligned with the spin axis and centred on the core, which is what you would expect from a dynamo operating in a spinning conducting fluid. Uranus throws that expectation out the window. Its magnetic field looks as though someone installed the dynamo off-centre and at a steep angle, and the resulting magnetosphere is a lopsided, wobbling structure that rotates in a complicated corkscrew pattern as the planet spins. You will encounter a similar magnetic oddity at Neptune, and together these two planets will force scientists to rethink their models of how planetary magnetic fields are generated. The prevailing theory for Uranus is that the dynamo operates not in the deep core, but in a shallower shell of electrically conducting fluid, possibly water, ammonia, and methane compressed into a superionic state, which would naturally produce the offset and tilt observed by Voyager. But this remains an area of active debate, and the fact that humanity has visited Uranus exactly once with a single spacecraft carrying 1970s technology means the data available to settle the argument is frustratingly sparse. Beneath the bland clouds, Voyager's instruments detect a surprisingly high temperature in the upper atmosphere that is difficult to explain by solar heating alone. Uranus also appears to radiate very little excess internal heat compared to Jupiter, Saturn and Neptune, which all emit significantly more energy than they receive from the Sun. Uranus, for reasons that remain unclear, seems to have a comparatively cold interior, or at least a very efficient insulating layer that traps its heat deep inside. Some researchers suggest that the catastrophic impact that tilted the planet may have disrupted normal convective heat flow, essentially locking the internal heat behind a stable stratified layer that prevents it from reaching the surface. Others argue that Uranus simply formed with less initial heat than its neighbours. The debate is one of those slow-burning mysteries in planetary science that may not be resolved until another spacecraft visits, which, given current mission timelines, could be decades away. You gaze at the smooth, blue-green disk of Uranus, a world that presents itself as the quietest giant in the solar system, but hides a scrambled magnetic field, a catastrophic tilt, and a thermal mystery beneath its placid face. The bland exterior, you're beginning to understand, is not the absence of something interesting. It is a mask. You turn away from Uranus's deceptively calm face and direct your attention toward its moons. Because if the planet itself is wearing a mask of blue-green indifference, its satellites are under no such obligation to behave politely. Voyager 2 discovers 10 new moons during the flyby, bringing the known total from 5 to 15, and while most of the newcomers are small, dark and unremarkable, icy boulders tumbling through Uranus's tilted system, the 5 major moons that were already known turn out to be far more interesting than anyone predicted, and one of them, the smallest of the 5, will produce images so bewildering that planetary geologists will spend decades trying to explain what they are looking at. Miranda. You need to hear that name and remember it, because Miranda is one of the most visually astonishing objects Voyager encounters on the entire mission. It is tiny, only about 470 kilometers in diameter, barely large enough to pull itself into a roughly spherical shape. Before the flyby, there is no particular reason to expect anything dramatic from a moon this small. Small moons are supposed to be simple, cratered, frozen, geologically inert. Miranda has not read the rulebook, as Voyager 2 sweeps past at a distance of roughly 29,000 kilometers, the closest approach to any of Uranus's moons. The cameras reveal a surface that looks like it was designed by a committee that could not agree on anything. There are ancient, heavily cratered plains sitting directly adjacent to vast tracts of bizarrely grooved and ridged terrain, unlike anything seen elsewhere in the solar system. These younger terrains, called coronae, are roughly oval-shaped regions dominated by concentric ridges and troughs that give them the appearance of enormous racetracks, or depending on your imagination, the layered cross-section of a sliced onion. The three major coronae, Arden, Elsinore and Inverness, named after locations in Shakespeare's plays, as all Uranian moons and their features follow a Shakespearean naming convention, are so sharply defined against the older cratered terrain that the boundaries look almost artificial, as though someone has cut and pasted geological provinces from different worlds onto the same small moon. And then there is Verona Rupes. You leaned forward for this one, because Verona Rupes is a cliff face that rises approximately 20 kilometers from base to crest, making it the tallest known cliff in the entire solar system. 20 kilometers. For comparison, the Grand Canyon is roughly 1.5 kilometers deep. The vertical face of El Capitan in Yosemite, which rock climbers consider one of the most imposing walls on Earth, is about 900 meters. Verona Rupes is more than 20 times that height, a sheer escarpment on a moon so small that its surface gravity is roughly 1/60th of Earth's. If you stepped off the edge, you would not plummet to your death in a dramatic Hollywood fashion. You would float downward in the feeble gravity for roughly 12 minutes before hitting the bottom, which somehow makes the whole thing more unsettling rather than less. 12 minutes of falling. On a moon smaller than some countries, the solar system has a talent for making you recalibrate your sense of scale. The question that Miranda poses is fundamental. How does a moon this small generate the geological energy required to produce such dramatic terrain? The coronae imply significant internal activity, some process that resurfaced large regions of the moon while leaving other regions untouched. The leading hypothesis for decades was that Miranda had been shattered by a massive impact and gravitationally reassembled, with the different terrain types representing incompletely mixed pieces of the original body. It was an evocative idea, a moon that had been broken and rebuilt, its surface a patchwork quilt of its own fragments. However, more recent modelling has largely moved away from this explanation. The current favoured theory involves tidal heating, the same mechanism that drives Io's volcanism and Europa's potential ocean. Miranda may have passed through a period of enhanced tidal interaction with other Uranian moons, generating enough internal heat to drive localised upwelling of warmer ice from the interior, producing the coronae as diapirs, blobs of buoyant material rising through the ice shell and spreading out on the surface like geological pancakes. Researchers still argue about the details. Was it a past orbital resonance with Umbriel or Ariel that provided the tidal kick? How long did the heating episode last? Why did it produce such sharply defined coronae rather than more gradual resurfacing? Miranda keeps its secrets well, and with only one flyby's worth of data, the answers remain provisional. The other four major moons, Ariel, Umbriel, Titania and Oberon, each offer their own quieter surprises. Ariel, the brightest of the five, displays extensive fault canyons and smooth plains that suggest relatively recent geological activity, though nothing as dramatic as Miranda's coronae. Its surface looks stretched and fractured, as though internal forces pulled the crust apart and allowed fresh material to fill in the gaps. Umbriel, by contrast, is the darkest of the major moons, its surface uniformly ancient and heavily cratered, with one mysterious bright feature on its equator, a ring-shaped marking informally called the fluorescent Cheerio by some members of the imaging team, though its official name is Wunder Crater. The origin of its brightness against Umbriel's otherwise uniformly dark surface remains unexplained. Titania is the largest of Uranus's moons, about 1,600 kilometers in diameter, and Voyager reveals a surface marked by enormous fault scarps and rift valleys indicating past tectonic activity. One canyon system, Messina Chasma, stretches nearly 1,500 kilometers across the surface, suggesting that Titania's interior expanded at some point, cracking the crust as it swelled. Oberon, the outermost of the five, is heavily cratered and ancient-looking, with a few large impact basins whose floors appear to have been flooded by some dark material, possibly cryovolcanic flows of water-ammonia mixtures that erupted from the interior and pooled in the low-lying areas before freezing solid. The Shakespearean names lend an oddly literary atmosphere to the geological descriptions. You find yourself reading about fault scarps on Titania and dark floored craters on Oberon as though leafing through a particularly violent act of a very cold play. You pull back and take in the Uranian moon system as a whole, 5 major moons each telling a different story about the interplay of internal heat, tidal forces, and the slow freezing of icy worlds. Miranda steals the spotlight with its impossible cliffs and patchwork terrain. But even the quieter moons carry evidence that the Uranian system was once more dynamic than its current placid appearance suggests. Somewhere in the deep past, these worlds were warmer, more active, more alive. Now they orbit in silence around a sideways planet, their stories frozen into ice and waiting for someone to come back and read them more carefully. You linger in the Uranian system a little longer, because the moons are not the only hidden treasure Voyager 2 uncovers here. The rings and the magnetosphere each have their own revelations, and together they paint a picture of a planet that is quietly, stubbornly defying every model that planetary scientists brought with them from Jupiter and Saturn. Uranus's rings were actually discovered before Voyager arrived, which is one of those satisfying instances where ground-based astronomy got there first. In 1977, astronomers James Elliott, Edward Dunham, and Jessica Mink were observing Uranus from the Kuiper Airborne Observatory, a modified cargo plane with a telescope mounted in it, which is exactly as improbable as it sounds, when they noticed that a distant star blinked on and off several times both before and after Uranus occulted it. The symmetric pattern of dimmings on either side of the planet could only mean one thing: rings. 9 narrow rings were identified from that single occultation observation, and 2 more were found in subsequent years. But the ground-based data could only tell you that the rings existed and roughly where they were. It could not tell you what they looked like, and Voyager 2's cameras reveal a ring system that is strikingly different from Saturn's opulent display. Where Saturn's rings are broad, bright, and made of reflective ice particles, Uranus's rings are narrow, dark, and made of material that reflects almost no sunlight. The particles are charcoal black, among the darkest objects in the solar system, probably composed of radiation-darkened organic compounds or carbon-rich material. The most prominent ring, the Epsilon ring, varies in width from about 20 to roughly 100 kilometers and is confined by 2 small shepherd moons, Cordelia and Ophelia, which Voyager discovers during the flyby. The other rings are even narrower, some only a few kilometers across, like dark threads stretched taut around the planet's equator. The whole system has a spare, austere quality, like the architectural drawings of someone who believes in minimalism. After Saturn's Baroque extravagance, Uranus's rings feel almost deliberately restrained. Voyager 2 also discovers 2 additional rings that ground-based observations had missed, bringing the total to 11. One of these, a broad, faint sheet of dust between the other rings, suggests that the ring system is more complex than the narrow main rings alone would indicate. The particles in the narrow rings are relatively large, centimeters to meters in size, while the dusty component contains much finer material. The sharp edges of the narrow rings are maintained by the shepherd moon mechanism that Voyager first confirmed at Saturn, but the overall darkness and narrowness of the Uranian rings raise questions about their origin and age that remain open. Are they ancient features as old as the planet itself? Or are they relatively recent, perhaps formed by the disruption of a small moon within the last few 100 million years? The darkness of the particles could be explained either way. Ancient exposure to radiation would darken almost any icy material, but freshly produced debris from a carbon-rich body could also start dark. Researchers continue to debate the ring's age, and without more data, the question resists a definitive answer. Now you turn to the magnetosphere, and this is where Uranus truly earns its reputation as the solar system's contrarian. Remember that scrambled magnetic field from the previous section, tilted 60 degrees from the spin axis and offset from the centre of the planet? Voyager 2 maps its consequences in real time as the spacecraft passes through the magnetosphere, and the result is unlike anything encountered at Jupiter or Saturn. Because the magnetic axis is so steeply inclined to the rotation axis, and because the rotation axis itself is tipped nearly parallel to the orbital plane, Uranus's magnetosphere does not form the stable, symmetric bubble you might expect. Instead, it wobbles and corkscrews as the planet rotates, the magnetic poles swinging wildly relative to the solar wind direction. At some points in Uranus's rotation, a magnetic pole faces the Sun. 90 degrees of rotation later, the equatorial region of the field faces the Sun instead. The resulting interaction with the solar wind is chaotic and time-dependent, creating a magnetosphere that essentially reinvents its geometry every 17 hours as the planet completes one rotation. Voyager's plasma and particle instruments detect a population of trapped charged particles within the magnetosphere, as expected, but the radiation environment is modest compared to Jupiter's intense belts. The charged particles appear to be primarily hydrogen ions, likely derived from the planet's extended hydrogen atmosphere and from the solar wind. One of the more intriguing findings is that the moons and rings embedded within the magnetosphere appear to sweep up charged particles as they orbit, creating detectable voids in the radiation belts at the orbital distances of the larger moons. These absorption signatures give scientists an indirect way to confirm the locations of moons and rings even without direct photographs. If you see a gap in the charged particle population at a specific radial distance, something is orbiting there and vacuuming up the particles. It is a beautifully indirect form of detection, like knowing someone has walked through a room because the dust has been disturbed. The fundamental question Uranus's magnetic field raises is about what generates it. The standard model for planetary magnetic fields, a convective dynamo in a metallic core, works well for Earth, Jupiter and Saturn. But Uranus's field, with its extreme tilt and offset, suggests a dynamo operating under very different conditions. The current leading model, as mentioned earlier, places the dynamo not in the deep core, but in a shallower layer of electrically conducting fluid, possibly a mixture of water, ammonia, and methane compressed into exotic high-pressure phases. In this intermediate zone, conditions may be just right for convection, and electrical conductivity to sustain a magnetic field, but the geometry of the convection would naturally produce a field that is tilted and offset from the planetary centre. It is an elegant hypothesis, but it is difficult to test with only one flyby's worth of magnetic data. Researchers still argue whether the shallow shell dynamo model is correct, or whether some other mechanism, perhaps a dynamo in a stably stratified core with unusual convective patterns, could produce the same observational signature. You take a final look at Uranus, that tilted, ring-wrapped, magnetically scrambled ice giant hanging in the dim outer solar system, and you appreciate how thoroughly it has upended expectations. Jupiter and Saturn, for all their grandeur, at least behaved in ways that existing theories could accommodate with modest adjustments. Uranus demands entirely new models. It is the planet that makes theorists earn their salaries, and it has done so on the basis of a single 6-hour flyby by a spacecraft designed in the early 1970s. You imagine what a dedicated Uranus orbiter might discover, spending years mapping that corkscrew magnetosphere, probing the atmosphere, and revisiting Miranda's impossible cliffs, and you feel a pang of something between longing and patience. For now, you let Voyager 2 carry you onward toward Neptune, where the solar system has one more ice giant waiting in the dark. You coast away from Uranus and begin the final planetary leg of the journey, a 3.5-year crossing to Neptune that will take Voyager 2 to the most distant planet it will ever visit. The Sun from out here is a brilliant star, but no longer anything you would call warm. Sunlight at Neptune is about 900 times dimmer than on Earth, which creates a serious practical problem for the imaging team. Voyager's cameras were designed for the brighter conditions at Jupiter and Saturn, and the dim light at Neptune means longer exposure times, which in turn means motion blur as the spacecraft hurtles past at nearly 98,000 kilometers per hour. Engineers at the Jet Propulsion Laboratory spend years developing a technique to compensate. They program the spacecraft to rotate slowly during each photograph, tracking the target the way a photographer pans a camera to keep a moving subject sharp. It is an elegant solution, executed by a machine with 69 kilobytes of memory, from a distance of over 4 billion kilometers, and it works beautifully. The Neptune images will be among the sharpest Voyager ever takes, which is a testament to the creativity of the engineering team, and a gentle rebuke to anyone who assumes old technology cannot learn new tricks. Voyager 2 makes its closest approach to Neptune on August 25, 1989, passing within roughly 5,000 kilometers of the planet's cloud tops, the closest flyby of any planet during the entire Voyager mission. And Neptune, unlike its bland cousin Uranus, greets you with drama. The first thing that commands your attention is the colour. Neptune is a deep, vivid, almost royal blue, significantly more saturated than Uranus's muted blue-green. The colour is again produced by methane in the atmosphere absorbing red light, but Neptune appears bluer than Uranus for reasons that are not entirely understood. Some additional atmospheric component or a difference in the vertical distribution of haze and cloud layers may be responsible for the deeper hue. Whatever the cause, the visual effect is striking. Neptune is gorgeous, the kind of planet that would sell posters even if it did nothing interesting, which it most certainly does. Because Neptune is not quiet, not even close. Voyager's cameras reveal a dynamic, turbulent atmosphere, decorated with discrete cloud features that stand in vivid contrast to Uranus's almost featureless disk. The most prominent is the Great Dark Spot, an enormous anticyclonic storm system in the southern hemisphere roughly the size of Earth. It sits at about 22 degrees south latitude, dark against the surrounding blue atmosphere, and it immediately invites comparison to Jupiter's Great Red Spot. The resemblance is more than cosmetic. Both are anticyclonic vortices embedded in banded atmospheric flow, but there are differences. the Great Dark Spot appears to change shape over the course of Voyager's observation period, elongating and contracting as it interacts with surrounding wind patterns. It is also accompanied by bright, high-altitude methane ice clouds that form along its southern and eastern boundaries, carried upward by the storm circulation and condensing in the cold upper atmosphere like cirrus clouds, forming at the edge of a terrestrial hurricane. These bright companions make the Great Dark Spot look almost three-dimensional in photographs, a dark hole in the blue atmosphere fringed with brilliant white streamers. Here is a mainstream historical fact that adds a twist to the story. When the Hubble Space Telescope observed Neptune in 1994, just 5 years after Voyager's flyby, the Great Dark Spot had vanished. Gone. A new dark spot had appeared in the northern hemisphere, but the original was simply no longer there. Unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's atmospheric storms appear to be transient, forming and dissipating on timescales of years rather than centuries. This raises intriguing questions about what drives Neptune's atmospheric dynamics and why its storms are so much more ephemeral than Jupiter's. Researchers still debate the underlying energy source. Neptune receives very little solar energy, yet its atmosphere is wildly active, which means the energy driving the weather must come primarily from inside the planet rather than from the sun. And that internal energy is one of Neptune's most fascinating characteristics. Unlike Uranus, which radiates only slightly more energy than it receives from the sun, Neptune radiates roughly 2.5 times more energy than it absorbs. Something inside Neptune is generating significant heat, most likely the slow gravitational contraction of the planet's interior, releasing potential energy as heat through a process called Kelvin-Helmholtz contraction. This internal heat source drives vigorous convection in the atmosphere, which in turn powers the storms and wind systems that Voyager observes. The contrast with Uranus is stark and unexplained. The two planets are near twins in size, mass, and composition, yet one is atmospherically comatose while the other is a raging dynamo. Why Uranus lacks significant internal heat emission remains one of the great unanswered questions of ice giant science, and the comparison between the two planets is one of the most valuable scientific legacies of Voyager 2's unprecedented visit to both. The winds are the other headline. Voyager measures wind speeds on Neptune that exceed 2,000 km per hour at certain latitudes, making them the fastest sustained winds ever recorded on any planet. This is deeply counterintuitive. You might expect that a planet farther from the Sun, receiving less energy, would have weaker atmospheric circulation. Earth's wind speeds max out around a few hundred kilometers per hour in the most extreme hurricanes. Neptune, sitting in the cold, dark fringes of the solar system, casually triples that. The explanation again comes back to internal heat and the dynamics of a deep, fluid atmosphere with relatively low friction. Neptune's atmosphere has very few solid surface features to disrupt airflow. There is no solid surface at all in the conventional sense, so winds, once established, encounter little resistance and can build to extraordinary speeds. There is a quirky analogy that meteorologists sometimes use. Neptune's atmosphere is like an ice rink where the skater has been given one good push and encounters almost no friction, so they just keep accelerating long after the initial impulse. It is an oversimplification, but it captures the essential physics of why an energy-poor planet can host energy-rich winds. You watch the Great Dark Spot rotate slowly in Voyager's image sequence, bright clouds scudding along its edges at terrifying velocities, the deep blue atmosphere swirling in patterns that are simultaneously familiar from Jupiter and utterly alien in their context. Neptune is the outermost giant, the last stop on the planetary tour, and it has proven itself the equal of its larger siblings in atmospheric complexity. You are 4.5 billion kilometers from home. watching weather on a world that takes 165 years to orbit the Sun, and the data is arriving at the speed of light but still taking over 4 hours to reach Earth. You're as far from home as any human instrument has ever been while still visiting a planet, and you're not done yet, because Neptune has a moon that is about to close the planetary chapter of the Voyager mission with one final unforgettable surprise. You pull your gaze away from Neptune's screaming winds and turn toward a moon that has no business being as interesting as it is. Triton is Neptune's largest satellite, roughly 2,700 kilometers in diameter, and it orbits the planet in the wrong direction. Every other large moon in the solar system orbits its parent planet in the same direction that the planet rotates, prograde, as celestial mechanicians call it. Triton orbits retrograde, moving against the flow of Neptune's rotation like a car driving the wrong way on a motorway. This single fact tells you almost everything you need to know about Triton's origin. It is not a moon that formed alongside Neptune from the same primordial disk of gas and dust. It is an interloper, a body that was born elsewhere and was gravitationally captured by Neptune at some point in the distant past. The most widely accepted theory is that Triton originated in the Kuiper Belt, the vast reservoir of icy bodies that extends beyond Neptune's orbit, and was snared by Neptune's gravity during a close encounter. Gravitational capture is not straightforward. An object flying past a planet on a hyperbolic trajectory will simply swing around and fly away again unless something removes enough energy to bind it into orbit. For Triton, the energy loss may have come from a collision with an existing Neptunian moon, or from tidal dissipation during a prolonged close encounter, or from interaction with a disk of gas that may have surrounded Neptune during its early history. Researchers still argue about which capture mechanism is most plausible, and the details matter because they determine how much tidal heating Triton would have experienced during the circularization of its initially eccentric orbit, which in turn affects how much geological activity the captured moon might have generated. Voyager 2 flies past Triton on August 25, 1989, passing within roughly 40,000 kilometers, and the images that come back are extraordinary. Triton's surface is young, diverse, and visually unlike any other moon Voyager has visited. The southern hemisphere, illuminated by weak sunlight at the time of the flyby, is covered by a bright polar cap of nitrogen and methane ice that gives the surface a pinkish hue. The colour coming from tholins, those same complex organic molecules produced by ultraviolet radiation acting on simple ices, the same chemistry you encountered on Titan. Outside the polar cap, the surface transitions into a bizarre terrain that the imaging team struggles to categorise. There are vast smooth plains that appear to have been flooded by cryovolcanic flows, eruptions not of molten rock but of liquid water, ammonia, or other volatile mixtures that froze solid on the surface. There are regions of wrinkled, dimpled terrain that someone on the team memorably describes as resembling the skin of a cantaloupe, and the name sticks. Cantaloupe terrain. It becomes an actual geological term which tells you something about the informality that creeps into nomenclature when scientists are confronted with features that have no precedent. The cantaloupe terrain is thought to result from diaparism, the upwelling of buoyant material from below, creating a pattern of roughly circular depressions separated by ridges, like a field of slow-motion bubbles frozen in mid-rise. The process is similar to what may have formed Miranda's coronae, though on a larger and more uniform scale. The implication is that Triton's interior was once warm enough to drive convective overturn in its ice shell, probably heated by the tidal forces generated during orbital circularization after its capture by Neptune. That tidal heating episode would have been intense and prolonged, potentially lasting hundreds of millions of years, and it may have been sufficient to maintain a subsurface ocean beneath the ice shell. Whether that ocean still exists today is an open question. Triton's orbit has long since circularized, so tidal heating has largely ceased. But radioactive decay in the rocky core may provide enough residual heat to keep a deep layer of water liquid. You are adding another world to the growing list of potential ocean-bearing moons in the outer solar system, and the list is getting long enough to feel less like a collection of exceptions and more like a rule. But the most dramatic discovery on Triton is happening right now, in the photographs Voyager is sending home. Dark streaks mar the bright southern polar cap, elongated smudges stretching downwind for over 100 kilometers across the nitrogen ice. At first they look like they could be surface features, dark material deposited by some ancient process. But closer analysis reveals that some of these streaks originate from discrete point sources, and the material appears to be suspended above the surface, carried by winds in Triton's extremely thin atmosphere. Voyager is looking at active geysers, nitrogen geysers, eruptions of gaseous nitrogen laced with dark dust particles, shooting upward roughly 8 kilometers into the thin atmosphere before being caught by prevailing winds and swept downwind in long dark plumes. Active geological processes on a moon 4.5 billion kilometers from the Sun, in an environment where the surface temperature is approximately minus 235 degrees Celsius, just 38 degrees above absolute zero. This is among the coldest surfaces in the solar system, and it is erupting. The mechanism behind the geysers is thought to involve a kind of solid-state greenhouse effect. Sunlight penetrates the translucent nitrogen ice of the polar cap, warming dark material beneath the surface. The trapped heat vaporizes nitrogen ice from below, building pressure until the gas erupts through the overlying ice layer like a champagne cork releasing, carrying dark subsurface material upward in the plume. It is a beautifully simple mechanism, requiring nothing more than sunlight, translucent ice, and a dark substrate, and it means that even at the coldest fringes of the solar system, where you might assume nothing could possibly be happening, nature finds a way to generate activity. There is a quirky footnote to this discovery. Triton's geysers were among the evidence that convinced scientists to look for similar activity on other icy worlds, and the eventual discovery of geysers on Enceladus by the Cassini spacecraft 2 decades later owed something to the mental framework that Triton established. Once you have seen nitrogen geysers at minus 235 degrees, water geysers at minus 200 seem almost predictable. You watch the dark plumes streak across Triton's pink-white polar cap in the Voyager photographs, delicate brushstrokes of geological activity on a canvas of frozen nitrogen, and you feel the weight of how far you have come. This is the last world Voyager 2 will visit. No more planets, no more moons rushing toward the camera in a blur of discovery. After Triton, the spacecraft turns its instruments toward the void and begins the long drift outward. But you linger for a moment, because Triton deserves it. A captured wanderer from the Kuiper Belt, scarred by tidal heating, coated in organic frost, and erupting gently into the thinnest of atmospheres at the edge of the known solar system. You're still savouring the image of Triton's dark plumes when Voyager 2's cameras catch one last set of surprises in the Neptunian system, the rings. Like Jupiter and Uranus before it, Neptune turns out to possess a ring system, and like those other ring systems, it has characteristics that nobody quite predicted. Ground-based observations in the 1980s had detected something around Neptune, but the results were confusing. Some stellar occultation experiments found evidence of material blocking starlight on one side of the planet but not the other, which made no sense for a complete ring. The data suggested arcs, partial rings, fragments of circles that existed only along portions of the orbit. This was theoretically problematic because ring arcs should not be stable. Orbital mechanics dictates that particles in an arc will gradually spread out along the orbit due to differential velocities and particle collisions, smearing the arc into a complete ring on relatively short timescales. And yet the occultation data stubbornly insisted that something arc-shaped was out there. Voyager 2 confirms the arcs and solves part of the mystery. Neptune has 5 principal rings, named after astronomers who contributed to the study of the planet: Gale, Leverrier, Lassell, Arago, and Adams. The outermost, the Adams ring, contains the famous arcs, 3 to 5 distinct concentrations of material embedded within an otherwise tenuous ring, like beads strung unevenly on a wire. The arcs are given names with a distinctly French flair: Liberté, Égalité, Fraternité, Courage, and one originally called Leading Arc that was later incorporated into the naming scheme. The names were proposed by the Discovery team, which included several French astronomers, and there is a certain grandeur to finding the motto of the French Revolution orbiting Neptune in the form of dusty ice clumps, 4.5 billion kilometers from Paris. The stability of the arcs is attributed to a gravitational resonance with Galatea, a small moon orbiting just inside the Adams ring. Galatea's gravitational influence creates a pattern of stable points along the ring where particles tend to accumulate, much like how gravitational resonances with moons create gaps in Saturn's rings, but working in reverse, confining material into clumps rather than clearing it out. The specific resonance is a 42 to 43 corrotation inclination resonance, which is exactly the kind of phrase that makes orbital dynamicists nod with satisfaction and everyone else reach for a glass of water. The essential point is that Galatea's gravity provides the gentle corralling force that prevents the arcs from spreading out, maintaining coherent structures within an otherwise diffuse ring. Researchers still argue about whether this resonance mechanism is sufficient to explain the longevity and sharpness of the arcs as observed by Voyager, because subsequent Hubble and ground-based observations have suggested that the arcs may be evolving, with some appearing to fade over time. If the arcs are not perfectly stable, they may be transient features that form and dissipate over decades or centuries, which would make them even more remarkable, snapshots of a dynamic process rather than permanent fixtures. The other Neptune rings are less dramatic but still scientifically valuable. The Leverrier ring is narrow and sharp-edged, reminiscent of some of Uranus's rings, while the Gale ring is broad and diffuse. The Lassell ring fills the space between Leverrier and Arago, forming a faint sheet of material. All of the rings are dark, composed of dust and small particles that reflect very little light, similar to the rings of Uranus and Jupiter. The common darkness of the ring systems around the 3 non-Saturn giant planets suggests a shared origin in the accumulation of radiation-darkened material, meteoritic debris, or the remnants of disrupted small moons. Saturn's rings, with their bright icy particles, remain the outlier, the one ring system that is both massive and reflective enough to be seen easily from Earth. Every other giant planet ring system requires a spacecraft or extremely clever ground-based observations to detect at all. Voyager 2 also refines the census of Neptune's moons during the flyby, discovering 6 previously unknown satellites in addition to the 2 already known, Triton and Nereid. The new moons are small, dark and irregularly shaped, ranging from roughly 50 to 400 kilometers in diameter. Most orbit close to the planet, deep within the ring system or just outside it, and several appear to interact gravitationally with the rings in ways that parallel the shepherd moon dynamics observed at Saturn and Uranus. Proteus, the largest of the newly discovered moons at about 420 kilometers across, turns out to be bigger than Nereid, which had been known since 1949. The fact that Proteus was not detected from Earth, despite being larger than the previously known Nereid, speaks to how dark these moons are, and how thoroughly they are lost in Neptune's glare when viewed from 4.5 billion kilometers away. Nereid itself remains an oddity. It has one of the most eccentric orbits of any known moon, swinging from about 1.5 million kilometres from Neptune at its closest to nearly 10 million kilometres at its farthest. The orbit is so elongated that some researchers have suggested Nereid may be a captured Kuiper belt object like Triton, though others argue it could be a regular Neptunian moon whose orbit was severely perturbed by the gravitational chaos of Triton's capture event. If Triton's arrival disrupted the existing moon system, and it almost certainly did, given that capturing a body as large as Triton would have scattered or destroyed most pre-existing moons, then Nereid may be a survivor of that upheaval, its orbit stretched and distorted by the gravitational convulsions that accompanied Neptune's acquisition of its largest satellite. Historians of planetary science note that Triton's capture may have been the single most transformative event in the Neptunian system's history, reshaping the moon population, generating enormous tidal heating, and possibly destroying an earlier ring system only for a new one to form from the debris. You take one last panoramic look at the Neptune system: blue planet, dark rings, arc-laden Adam's ring, a retinue of small dark moons, and Triton retreating behind you with its geyser plumes still drifting across the polar cap. This is the end of the planetary road. Voyager 2 has now visited all 4 giant planets, a feat that no other spacecraft has accomplished, and that the orbital mechanics of the solar system will not permit again for over a century. You feel the finality of the moment settle around you like a blanket, and you let Voyager carry you past Neptune's orbit and into the space beyond, where the sun is just another star and the planets are memories dissolving into the dark. You drift away from Neptune and its arc-laden rings, and the planetary tour is over, but the mission is not. There is something riding on the side of each spacecraft that has nothing to do with magnetometers or infrared spectrometers, and it deserves its own moment in the quiet dark. You remember that golden record, the one bolted to the exterior of both Voyagers before launch, the 12-inch gold-plated copper disc that Carl Sagan and his committee assembled as a message to anyone or anything that might stumble upon the spacecraft in the distant future. Now, with no more planets to visit and the void stretching ahead in every direction, it feels like the right time to sit with that record and understand what is actually on it and why it matters. The project began in early 1977, when NASA gave Sagan approximately 6 weeks to assemble the contents of what would become humanity's most far-flung calling card. The timeline was absurd. 6 weeks to represent an entire civilization, every culture, every language, every piece of music, every landscape, every emotion, compressed onto a single phonograph record that would need to be playable by beings who might have no concept of sound, sight, or human biology. Sagan recruited a small team that included writer Juvian, artist John Lomberg, science journalist Timothy Ferris, and several others. The pressure was immense and the debates were passionate, because every inclusion implied 1,000 exclusions, and every exclusion felt like a betrayal of some corner of human experience. The record contains 115 images encoded as analog signals. These include photographs of mathematical definitions, the solar system, human anatomy, DNA structure, landscapes from every continent, cities, architecture, food, animals, and people of various ages and ethnicities engaged in daily activities. There is a photograph of a woman nursing an infant, a man eating a piece of fruit, children studying a globe. The images progress from scientific basics, circles, chemical definitions, the position of the sun in the galaxy, to increasingly human and emotional content, as though the record is slowly introducing its finder to the species that made it, starting with universal truths and building toward the particular and personal. One quirky inclusion that Sagan's team debated fiercely was whether to include an image of a nude man and woman. NASA, still bruised from controversy over the nude figures on the earlier Pioneer plaques, was cautious. The compromise was to include a silhouette drawing rather than a photograph, which satisfied the anatomical information argument while sidestepping the modesty objection. Researchers and cultural historians still argue whether the decision was a reasonable accommodation of 1970s American sensibilities or a slightly absurd act of prudishness directed at hypothetical aliens who almost certainly have no concept of human nudity taboos. The audio portion of the record is divided into 3 categories: greetings, sounds, and music. The greetings come in 55 languages, ranging from ancient Sumerian to modern Mandarin, each one a brief spoken message of goodwill from humanity. The oldest language represented is Akkadian, a language that has been dead for roughly 2,000 years, which lends the greeting section a temporal depth that stretches back to the dawn of written civilization. There is also a greeting from a humpback whale, included among the languages without further comment, which is either a touching gesture of interspecies solidarity or a mildly presumptuous claim that whale song constitutes a language. Either way, the whale gets its say. The Sounds of Earth section includes natural sounds, wind, thunder, surf, bird song, the calls of animals, as well as human-made sounds, footsteps, heartbeats, laughter, the sound of a kiss, a mother's first words to a newborn baby, and a progression of transportation sounds from horse and cart to jet airplane. The sequence is designed to convey the texture of life on Earth, the ambient soundtrack of a living planet. There is a recording of brainwaves, specifically the brainwaves of Andruyan, recorded shortly after she and Sagan had privately declared their love for each other. Druyan later described meditating during the recording on the history of Earth, the evolution of life, and her newly discovered love, hoping that the electrical patterns of her thoughts might somehow encode these feelings into the data. Whether an alien civilization could extract emotional content from a human electroencephalogram is, to put it mildly, debatable. But the gesture is so profoundly human, the hope that love can be transmitted as a signal, that its scientific plausibility almost does not matter. The music selection consumed more debate than any other element. The final playlist spans cultures and centuries. Bach's Brandenburg Concerto No. 2, Mozart's Magic Flute, Beethoven's Fifth Symphony, a Navajo night chant, a Peruvian wedding song, a Georgian chorus, Indian raga, Javanese gamelan, Senegalese percussion, Louis Armstrong's Melancholy Blues, and Chuck Berry's Johnny B. Good. The inclusion of rock and roll was initially resisted by some committee members who felt it was too lowbrow for an interstellar message. Sagan reportedly quipped that the problem with rock and roll was not that it was unfit for the cosmos, but that the cosmos was perhaps unready for it. Historians still argue whether the playlist adequately represents the breadth of human musical achievement, or whether it is inevitably skewed toward the tastes and biases of its American curators. Entire swathes of musical tradition are absent. No Chinese opera, no Aboriginal Australian music, no hip-hop. Though to be fair, hip-hop was barely a year old when the record was assembled. The record's aluminum cover includes a set of pictographic instructions for playing the disc, along with a diagram showing the position of the Sun relative to 14 pulsars, rapidly rotating neutron stars whose precise frequencies serve as a kind of cosmic address, allowing the finder to triangulate the Sun's location in the galaxy, and even determine when the spacecraft was launched based on the known spin-down rates of the pulsars. It is an elegant piece of scientific communication, though some researchers have questioned whether an alien civilization would interpret the diagrams correctly, or whether the entire encoding scheme reflects assumptions about perception and cognition that are deeply human. You sit with the golden record for a long, quiet moment, imagining it fixed to the side of a spacecraft that is now drifting between the stars. Nobody will play it for millions of years, if ever, The odds of either Voyager being found by an extraterrestrial civilization are so remote that the record is, in practical terms, a gesture rather than a communication. But gestures matter. The golden record is less a message to aliens than a message to ourselves, a declaration that in 1977, a small group of humans thought it was worth the effort to say hello to the universe, just in case someone was listening. You let the golden record rest in your thoughts and turn your attention forward, because both Voyagers are still travelling, still transmitting, and still doing science. The planetary flybys may be over, but the mission has quietly entered a new phase that many scientists consider just as important as the grand tour itself. The question is no longer, what do the planets look like up close? But rather, where does the sun's influence end and interstellar space begin? You are riding Voyager 1 now, the faster of the two, heading roughly northward out of the ecliptic plane at about 17 kilometers per second, and you're approaching a boundary that no human-made object has ever crossed. To understand what Voyager is about to encounter, you need to picture the heliosphere. The sun does not just emit light and heat. It continuously blows a stream of charged particles, protons, electrons, and heavier ions, outward in every direction, at speeds ranging from roughly 300 to 800 kilometers per second. This solar wind inflates a vast bubble around the sun, a cavity in the interstellar medium called the Heliosphere, inside which the sun's magnetic field and particle output dominate the local environment. Outside the heliosphere, the galaxy takes over. Interstellar gas, cosmic rays from distant supernovae, and the magnetic field of the Milky Way itself. The boundary between these two regimes is not a sharp line but a series of transitional zones, and Voyager 1 is about to pass through them one by one. The first boundary is the termination shock, the point where the solar wind abruptly slows from supersonic to subsonic speed as it begins to feel the pressure of the interstellar medium pushing back. Think of it like the shock wave that forms ahead of a jet breaking the sound barrier, but in reverse. The solar wind is decelerating from its own version of supersonic flow. Voyager 1 crosses the termination shock in December of 2004, at a distance of approximately 94 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, so Voyager is now 94 times farther from the Sun than you are, which is a number that sounds tidy on paper, but becomes genuinely disorienting if you try to visualize it. The crossing is detected not as a single dramatic moment, but as a series of changes in the particle and magnetic field data. The solar wind speed drops, the magnetic field strength increases, and the population of energetic particles shifts. Researchers analysing the data initially debate whether Voyager has actually crossed the termination shock or merely encountered a transient fluctuation, because the boundary turns out to be more dynamic and messy than theoretical models predicted. It ripples, it moves, it breathes in and out in response to changes in solar activity, and Voyager may have crossed it multiple times as it sloshed back and forth over the spacecraft. Beyond the termination shock lies the heliosheath, a turbulent region where the slowed solar wind piles up and becomes compressed, heated, and chaotic. You spend years crossing this region. It is far thicker than anyone expected, and the data Voyager sends back paints a picture of a frothy, magnetic mess. The magnetic field direction fluctuates wildly. The particle populations are a confused mixture of solar and interstellar origin. The heliosheath is not the orderly transition zone that textbook diagrams suggest. It is a roiling frontier, a no-man's land between stellar and galactic dominion, and Voyager is wading through it with the patient determination of a machine that does not know how to stop. The final boundary is the heliopause itself, the outer edge of the heliosphere where the solar wind's outward pressure is finally balanced by the inward pressure of the interstellar medium. Beyond the heliopause, you're in interstellar space, the space between the stars. Voyager 1 crosses this boundary on August 25th, 2012, at a distance of approximately 121 astronomical units from the Sun. The date is significant not just scientifically but symbolically. It is the first time a human-made object has left the Sun's protective bubble and entered the true space between stars. The announcement, when it comes, is preceded by months of careful analysis and vigorous debate among the Voyager science team, because the heliopause crossing is not as clean as anyone hoped. The expected signature of crossing the heliopause was a simultaneous change in 3 measurements: a drop in solar particle intensity, a rise in galactic cosmic ray intensity, and a change in the direction of the magnetic field from the Sun's orientation to the interstellar field's orientation. Voyager 1 detects the first 2 changes clearly. Solar particles plummet and cosmic rays surge, but the magnetic field direction does not rotate as dramatically as predicted. It changes somewhat, but not by the 90-degree or larger shift that many models forecast. This discrepancy sparks intense debate. Some researchers argue that Voyager has indeed crossed the heliopause and that the magnetic field models were simply wrong about the expected direction of the interstellar field. Others suggest that Voyager might be in some previously unknown transitional region that is neither fully heliospheric nor fully interstellar. The argument continues for over a year before a coronal mass ejection from the Sun reaches Voyager's location and causes oscillations in the local plasma that allow scientists to measure the plasma density directly. The density is consistent with interstellar space, roughly 40 times higher than the heliosheath, and the debate is largely settled. Voyager 1 is officially in interstellar space. You feel the significance of that sentence, even through the drowsiness that is probably settling over you by now. A machine built in the 1970s, carrying the processing power of a basic calculator, has left the solar system's magnetic bubble and is swimming in the thin, cold plasma between the stars. The Sun is still visible from Voyager's perspective. It will remain the brightest star in the sky for a very long time, but its wind no longer reaches here. You're beyond the breath of your own star, riding a spacecraft that is moving at roughly 61,000 kilometers per hour, and yet will not reach the nearest star for another 40,000 years. The scale is numbing. You let it wash over you like a warm tide and feel your grip on wakefulness soften just a little. You leave Voyager 1 drifting in interstellar space and loop back to check on its sibling, because Voyager 2 has its own date with the heliopause, and its crossing will reveal something that nobody fully anticipated. The Sun's protective bubble is not symmetrical. It is dented, squished, and dynamic in ways that a single data point from Voyager 1 could never have shown. You need both spacecraft exiting the heliosphere at different locations and different times to see the full picture, and the full picture is wonderfully messy. Voyager 2 crosses the termination shock on August 30th, 2007, roughly 3 years after Voyager 1, at a distance of approximately 84 astronomical units from the Sun. That number should catch your attention, because Voyager 1 crossed the same boundary at 94 astronomical units. A difference of 10 astronomical units, roughly 1.5 billion kilometers, between the 2 crossing points means that the termination shock is significantly closer to the Sun in the direction Voyager 2 is travelling, which is roughly southward out of the ecliptic plane, than in the direction Voyager 1 is heading northward. The heliosphere, it turns out, is not a nice round bubble. It is asymmetric, compressed on one side and extended on the other, shaped by the pressure of the local interstellar medium flowing past it, and by variations in the solar wind output at different latitudes. Imagine blowing a soap bubble while walking into a breeze. The bubble gets pushed back on the windward side and stretches out on the leeward side. The Heliosphere does something similar as the Sun moves through the interstellar medium at roughly 26 kilometers per second, creating a compressed nose in the upstream direction and an elongated tail downstream. Voyager 2 then spends over a decade crossing the heliosheath, just as Voyager 1 did, and the data it sends back tells a complementary but distinctly different story. The particle populations, magnetic field strengths, and plasma conditions in Voyager 2's heliosheath are measurably different from what Voyager 1 encountered, confirming that the heliosheath is not a uniform region, but a complex, spatially varying environment. The two Voyagers are essentially taking core samples of the Sun's outer boundary at different locations, and every difference between their measurements teaches scientists something new about the three-dimensional structure of the heliosphere. Voyager 2 finally crosses the heliopause on November 5, 2018, becoming the second human-made object to enter interstellar space, at a distance of approximately 119 astronomical units from the Sun. The crossing is cleaner in some respects than Voyager 1's. Voyager 2 carries a working plasma science instrument, a device that directly measures the properties of the surrounding plasma, which Voyager 1's equivalent instrument had stopped functioning decades earlier. This means Voyager 2 can directly detect the sharp increase in plasma density that marks the transition from heliosheath to interstellar space, providing the most unambiguous measurement of the heliopause crossing that either spacecraft has achieved. The data shows a dramatic jump. The plasma density increases by roughly 20 times within a very short distance, confirming that the heliopause is a relatively sharp boundary rather than a gradual fade. But here is where it gets truly interesting. Voyager 2 crosses the heliopause at 119 astronomical units, compared to Voyager 1's 121. Again, the asymmetry. The heliosphere is smaller in Voyager 2's direction of travel. The two crossing distances, combined with the termination shock asymmetry, allow scientists to begin constructing a rough three-dimensional model of the heliosphere's shape, and the emerging picture is more complex than the simple elongated bubble that older models assumed. Some researchers have proposed that the heliosphere may not have a long comet-like tail at all, but might instead be shaped more like a deflated croissant or a rounded tailless shell, compressed relatively symmetrically by the interstellar medium. This remains one of the most actively debated topics in heliophysics. Historians of science note that the entire modern understanding of the heliosphere's shape rests on exactly two data points, the two Voyager crossings, which is an extraordinarily thin empirical foundation for such a fundamental piece of solar system architecture. Every model is essentially an extrapolation from two measurements taken by spacecraft designed before anyone had email. The interstellar medium that Voyager 2 enters turns out to have its own characteristics worth noting. The plasma is thin but detectable, roughly 0.05 ions per cubic centimetre, which is dense by interstellar standards, suggesting that the Sun resides in a relatively warm, partially ionized region of the galaxy called the local interstellar cloud. The magnetic field direction in the interstellar medium is slightly different from what Voyager 1 measured, hinting at small-scale structure in the galactic magnetic field that had not been previously detected. There is a quirky and humbling realization embedded in this data. The interstellar medium is not featureless emptiness. It has texture, density variations, magnetic structure, and its own dynamics that operate on scales vastly larger than the solar system. The Voyagers are essentially dipping their toes into a galactic ocean and reporting back on the temperature and salinity of the shallows. One of the more surprising findings from both Voyager heliopause crossings is the existence of a cosmic ray boundary layer just outside the heliopause. Both spacecraft detected a region where cosmic ray intensities continue to increase even after the solar particle flux had dropped to near zero, suggesting that the heliopause is embedded within a broader transition zone where galactic and solar influences overlap in complex ways. Researchers still argue about the physical processes operating in this boundary layer, whether it represents a pile-up of cosmic rays deflected by the heliosphere's magnetic draping, or a natural gradient in the interstellar cosmic ray population, or something else entirely. The data is tantalizing but sparse, and with both Voyagers moving ever outward, the opportunity to study this boundary layer in detail is slowly receding. You sit with a picture that is emerging. Two spacecraft launched within weeks of each other in 1977, crossing the edge of the solar system at different points, different times and different conditions, and together sketching the first crude map of humanity's magnetic border with the galaxy. It is a map drawn with only 2 pins, but those 2 pins have told us that the border is asymmetric, dynamic, sharper than expected in some ways, and fuzzier than expected in others, and embedded within an interstellar environment that is anything but empty. You feel grateful for the redundancy of having 2 spacecraft, because without Voyager 2's complementary crossing, the picture from Voyager 1 alone would have been misleadingly simple. The universe, as usual, rewards those who look from more than one angle. You have spent a long time now riding these 2 spacecraft through the solar system and beyond, watching them photograph volcanoes, rings, storms and geysers, and then push through the sun's magnetic skin into the galaxy. But there is a story you have not yet fully appreciated, one that runs quietly beneath every discovery and every photograph, and it is the story of the people who have kept these machines alive. Because here is the thing about Voyager 1 and Voyager 2 that borders on the miraculous. They are still functioning, decades after launch, billions of kilometers from home, running on technology that predates the personal computer. Both spacecraft continue to transmit data back to Earth. And the only reason they do is because a small dedicated team of engineers at the Jet Propulsion Laboratory has spent nearly half a century performing what might be the longest running act of mechanical life support in human history. The power source is the most fundamental constraint. Each Voyager carries 3 radioisotope thermoelectric generators, devices that convert heat from the natural decay of plutonium-238 into electricity. There are no solar panels. At Uranus's distance and beyond, the sun is too faint to generate useful solar power, and there are no backup batteries. The RTGs are it. When they run out, the mission ends. The problem is that plutonium-238 has a half-life of roughly 87 years, which means the power output decreases by about 4 watts per year. At launch, the 3 RTGs on each spacecraft collectively produced approximately 470 watts. By the time you're listening to this, that figure has dropped below 300, and it continues to fall. Engineers have responded to this slow energy death with a decades-long campaign of triage, systematically shutting down instruments and heaters to conserve power for the equipment that is still doing useful science. The cameras were turned off after Neptune. There's nothing close enough to photograph in interstellar space, and the power they draw is needed elsewhere. Heaters for various instrument platforms have been switched off one by one, allowing those components to cool to temperatures far below their designed operating limits. The fact that they continue to function in this frozen state is a testament to the over-engineering of 1970s spacecraft hardware, built with margins that their designers probably never imagined would be tested this thoroughly. The communication system's another quiet marvel. Voyager transmits data using a 23-watt radio transmitter, roughly the power of a refrigerator light bulb, and the signal it sends across billions of kilometers is unfathomably faint by the time it reaches Earth. The Deep Space Network, NASA's array of massive radio antennas in California, Spain and Australia, picks up a signal that has spread across such an enormous volume of space that the received power is measured in fractions of a billionth of a watt. extracting meaningful data from a signal that weak requires extraordinary precision in antenna pointing, signal processing, and error correction. The data rate has been reduced over the years as the distance has grown, from the relatively brisk 4800 bits per second used during the Neptune flyby, down to about 160 bits per second for current interstellar data. At that rate, transmitting a single smartphone photograph would take several weeks, but the link holds. Every day, for a few hours, one of the Deep Space Network antennas points at a spot in the sky where a tiny spacecraft is sailing through interstellar space, and data trickles in. Software updates are perhaps the most remarkable aspect of the ongoing engineering effort. Over the course of the mission, the Voyager team has uploaded new software to the spacecraft multiple times, reprogramming their onboard computers from billions of kilometers away to handle situations the original designers never anticipated. Remember the image motion compensation technique that allowed Voyager 2 to take sharp photographs in Neptune's dim light? That was a software patch, uploaded across the solar system and executed by a computer with less memory than a modern kitchen appliance. When Voyager 2's scan platform jammed at Saturn, engineers diagnosed the problem remotely and developed new operating procedures that were uploaded as software commands. When the spacecraft's primary thrusters began degrading from years of use, engineers switched to backup thrusters that had been idle since 1981, and those backups worked. There is a quirky and somewhat alarming detail here. The engineers who currently maintain Voyager are, in some cases, working with documentation and code written by people who have long since retired or passed away. The institutional knowledge required to operate these spacecraft exists in a thin chain of human memory and handwritten notes that stretches back to the Nixon administration. Historians of technology argue that Voyager represents one of the longest continuous operational relationships between humans and a single machine, and the challenge of preserving the expertise to maintain it is itself a fascinating case study in organizational memory. The thrusters deserve their own moment. In 2017, NASA announced that Voyager 1's primary attitude control thrusters, the ones that keep the antenna pointed at Earth, had degraded to the point where they were no longer reliable. Without attitude control, the antenna would drift off target and the communication link would be lost. Engineers decided to try activating a set of trajectory correction thrusters that had not been fired since 1980, 37 years earlier. These thrusters were designed for a different purpose: course corrections during planetary flybys, and had never been tested for the delicate, short pulses needed for attitude control. The team dug through decades-old documentation, wrote new commands in an obsolete programming language, uploaded the instructions across 20 billion kilometers of space, and waited the 19 hours and 35 minutes it took for the command to reach the spacecraft and the confirmation to travel back. The thrusters fired perfectly. A set of rocket nozzles that had been dormant since before many of the current engineers were born responded to a command from Earth and kept the mission alive. You can almost hear the cheering at JPL from here. The ongoing science is modest compared to the planetary flyby era, but uniquely valuable. Both Voyagers continue to measure the properties of the interstellar medium: plasma density, magnetic field strength and direction, cosmic ray intensity and composition, data that cannot be obtained from any other source because no other spacecraft is out there. Every measurement they take is the first and only in situ observation of the local interstellar environment, and it will remain so until another mission follows them into the void, which is not expected for decades. Researchers use this data to refine models of the Heliosphere, the interstellar medium, and the Sun's interaction with the galaxy, and every year the data becomes more precious as the Voyagers move deeper into unexplored space. You think about the handful of engineers sitting in a control room at JPL, sending commands to machines older than some of their own parents, coaxing a few more months, a few more years, a few more watts out of decaying plutonium and aging transistors. There is something deeply human about refusing to let go, about pouring creativity and care into a machine that by all reasonable expectations should have died decades ago. The Voyagers persist because people insist that they persist, and that insistence is, in its own quiet way, as remarkable as any photograph of Jupiter's storms or Saturn's rings. You release your grip on the engineering manuals and the thruster diagnostics and the power budgets, and you let both Voyagers drift. They are moving away from the Sun at this very moment, Voyager 1 heading roughly in the direction of the constellation Ophiuchus at about 17 kilometers per second, Voyager 2 heading toward the constellation Sagittarius at about 15 kilometers per second. Neither spacecraft is aimed at any particular star. Their trajectories were determined by the gravitational slingshots of the planetary flybys, not by any deliberate targeting of a stellar destination. But the universe is full of stars, and if you wait long enough, the Voyagers will eventually drift into the neighbourhoods of other suns. Voyager 1 will pass within about 1.6 light-years of a star called Geyser 445 in roughly 40,000 years. Voyager 2 will approach a star called Ross 248 in about the same time frame. Neither spacecraft will be functioning by then. The plutonium will have decayed to silence, the transmitters will have gone dark, and the computers will have long since frozen into inert blocks of 1970s silicon. What will remain is the structure, the aluminum, the titanium, the gold-plated copper of the record, the magnesium framework, drifting in the vacuum where there is no air to corrode, no weather to erode, no organisms to decompose. The Voyagers will outlast every building currently standing on Earth. They will outlast most geological features on the planet's surface. In the cold, empty cathedral of interstellar space, they will endure for hundreds of millions of years, perhaps billions, slowly weathered by cosmic rays and micrometeorite dust, but essentially intact, carrying their golden records through a silence so profound that the concept of sound loses meaning. There is a famous photograph that speaks to this future, and it was not taken during any planetary flyby. On February 14, 1990, as Voyager 1 was sailing beyond Neptune's orbit on its way out of the solar system, Carl Sagan persuaded NASA to turn the camera around and take one last photograph of Earth. The result is known as the pale blue dot, a single pixel of blue-white light suspended in a sunbeam against the blackness of space, taken from a distance of about 6 billion kilometers. It is arguably the most important photograph ever taken, not for its scientific content, which is essentially zero, but for its philosophical payload. Every human being who has ever lived, every war and love affair and cathedral and extinction, is contained in that single bright speck. Sagan wrote about it with characteristic eloquence, and his words have become a kind of secular prayer for the space age. Researchers and historians still argue whether the pale blue dot image represents the pinnacle of Voyager's cultural legacy, or whether the golden record holds that distinction. But the two are really part of the same impulse, the urge to see ourselves from the outside, to understand our place in the universe by stepping far enough away that the whole picture fits in the frame. The Voyager missions have shaped planetary science in ways that ripple forward through every subsequent mission. The discovery of Io's volcanism led directly to the study of tidal heating as a major geological force, which underpins the current scientific excitement about ocean worlds like Europa and Enceladus. The revelation of Titan's thick atmosphere inspired the Cassini-Huygens mission, which became one of the most successful planetary missions ever flown. The characterization of Uranus's and Neptune's scramble magnetic fields reshaped dynamo theory and highlighted the ice giants as a distinct and poorly understood class of planet. The detection of Neptune's ring arcs advanced the study of gravitational resonances in disk systems. The crossing of the heliopause provided the first empirical data on the boundary between stellar and interstellar space, a boundary that had been theorized for decades but never measured. Every one of these legacies traces back to 2 spacecraft that cost, in total, roughly the price of a single modern sports stadium, launched in a year when the most advanced consumer technology was an 8-track tape player. And the golden record endures as something more than science. It is a philosophical artifact, a statement of intent from a species that knew the odds of the record being found were essentially zero but decided to make it anyway. The record says we were here, we made music, we loved each other, we looked up at the stars and wondered. It carries Chuck Berry and Beethoven and the sound of a mother greeting her newborn child, and it is sailing through interstellar space right now, at this moment, while you listen to these words. There's a line from Anne Druyan that captures the spirit of the project better than any technical description. She described the record as a kind of love letter cast into the cosmic ocean, and that metaphor holds up beautifully across the decades. The Voyagers are bottles thrown from a very small island into a very large sea, and the message inside is not a plea for rescue, but a simple, hopeful hello. You lean back now. The journey's over, or at least your part of it is. The Voyagers will continue long after you fall asleep, long after everyone alive today is gone, long after the languages on the golden record have evolved beyond recognition or fallen silent. They will drift through the Milky Way as the sun ages and swells and eventually exhausts its fuel, as the continents on Earth rearrange themselves and the oceans rise and fall, as civilizations you cannot imagine emerge and flourish and fade. The spacecraft will still be out there, silent, golden, carrying their cargo of music and images and whale song and brain waves into a future that no model can predict. And now, gently you let the journey settle. The images of Jupiter's swirling storms soften in your mind, blending with the pale blue cracks of Europa and the orange haze of Triton. Saturn's rings thin to a whisper, and Miranda's cliffs recede into a peaceful blur. Neptune's blue deepens into something warm and sleepy, and Triton's geysers slow to a gentle exhale, like breath on a cold morning fading into still air. The solar wind quiets, the heliopause thins to nothing. The stars outside are patient and unimaginably distant, and among them, 2 small machines glide onward, carrying everything we are into everything we do not yet know. The golden records turn silently in their aluminum covers, waiting, and the universe stretches ahead in every direction, vast and dark and full of the kind of quiet that is not empty but simply resting. You are resting too now. Your eyelids are heavy with the weight of 4 planets, dozens of moons, 115 photographs of home, and the longest road trip ever taken. Let it go. Let the Voyagers carry the rest. They know the way, even if nobody has mapped it yet, and they will keep going long after the last light in your room dims to nothing. Breathe in slowly, breathe out slower, and drift, the way they drift, calmly, steadily, into the deep and endless night.